Anything is right stream. Ty, rezonans Kielce tutaj.
Dobrze. Well, dear colleagues, it's time to start our meeting, though I don't see some key persons for the first half of our day. However, we'll hope they will appear soon. Welcome to this online conference, which is organized instead of the last year meeting, which was planned in Moscow in Russia with a field trip over Volga River. However, you all know what happened last year and continues this year. Therefore, we can meet only online, but this is also not bad, I think. After this short introduction, let me pass the word to Tomasz Kaliski, the chair of the flag board, to tell us a few words about how flag survived in these COVID times. Please, Tomasz. Tomasz is in the field now, and he has problems with internet connection, but tomorrow he will be fully with us. Now only for 5 to 10 minutes. Thank you, Tomasz, that you managed to link to us. Okay.
Okay, thank you very much. Welcome for everybody online. We are in the very important international meeting point in Poland, but without Wi-Fi. Here is the chair from Norway. There is a lot of tourists and also students from the different countries. But welcome for the all people online on this flag meeting from, I don't know, from Moscow probably, but theoretically or in internet generally. Okay, then we have no very hard period for flag events for general for the people, and our connection was broken in many places. That was the very hard period, not only for the general for the people, but also I know that some people from our organization have a very hard periods. Also me during these last practically 3 years from Belgium symposium. Yeah, we delay 1 year if you're looking on the Russian symposium, But anyway, I hope that what we discuss in board, the next meeting, but not online, will be in Moscow and will be in Russia in the Upper Volga basin. I hope it will be possible in the next year. Yeah, but no, we will see what will be with this COVID-19. If you're looking on the activity, we have practically some papers in the geomorphology. There is the volume of the last symposium, and we plan also the publish the next volume after this meeting. Yeah, I hope that the connection will be much better than from Karpacz, where I am, because no, I am on mobile, yeah, and therefore, but tomorrow we or today we plan come back to Kielce University. This is only 500 kilometers from Russia. Is nothing for Europe. Is enough. Yeah, but I hope that tomorrow I will be in normal condition and we connect with all. Anyway, I wish you in this day and I hope in the next day also the very good papers and very good oral presentation. And I hope we can discuss some problems also in the general discussion tomorrow. Yeah. Okay, that's all I think.
Okay, thank you, Tomasz, and see you tomorrow for the full day. And also we will have the record of the conference, which may be distributed after. Also, if you miss some interesting presentations, you can download the record and watch it after all. Well, okay. Dear colleagues, in the last month, the flag community have lost one of its active members, I mean Rob Westaway, and we asked David Bridgeland to say a few words in memory of him. Well, David.
Okay, I've unmuted. Can everybody hear me?
Yes.
Now, you caught me on the hop a bit, Andre, and I don't know if I'm the only one here, because I thought you were starting at 9 o'clock GMT.
Well, it was a confusion of time. I have
GMT is our winter time, and it's only 8 o'clock.
Yeah, but in the program which was sent yesterday, you see there are 3 columns. There is London time, then Paris.
Okay. Well, unfortunately, I didn't look at that very closely, Andre. So, I'm, as you can see from this pillow, I'm still in bed, although I have dressed. I got this message saying starting in 3 minutes, and that was 12 minutes ago. So anyway, this shouldn't be about me. This is about our friend Rob Westaway. But I've also I'm also giving a 20-minute the first session shortly on Rob's contribution. So those who don't know Rob came into the quaternary world through an interest in uplift when he realized that people like Daryl Maddy, who was one of the founder members of FLAG, and I were promoting uplift as a fundamental factor behind the existence of river terraces, the existence of staircases of river terraces in many parts of the world. And Rob had already formulated some ideas about this based on his understanding of uplift and his ideas about the crust. And he had some ideas which I think were very controversial at the time and are still pretty controversial. And he backed them up with some complex mathematics and computer modeling, which most of us working in the quaternary couldn't understand, it's probably fair to say. And the thing that impressed me was that his ideas could explain things that were unable to be explained by others, particularly lots of people modeling uplift using the mantle and working mostly on sea level in short-term quaternary timescales, such as really the sea level since deglaciation at the end of the last MIS2, essentially. Not terribly interested in the longer timescale, apt to dismiss our puzzle about river terraces. And so how can you explain these river terraces? Oh, I don't know, I haven't really thought about that. Rob was into all this. Rob became an enthusiastic member of the community and a regular attender of flag meetings, and he's attended many flag meetings, and those of you who've been to them will remember perhaps quaking in your boots hoping that Rob wouldn't ask you a question at the end of your presentation, because he was fearsome and dare I say sometimes slightly rude. He seemed rude. He was always kind, and if you met him and discussed things in conversation with him, he was kind and friendly and keen to explain, but he was fearsome, and he didn't respect authority and status, and so he was something of a maverick, but he enlivened our meetings enormously when he attended, and I think we're going to miss him hugely, because his energy was something that we valued and benefited from, I think. He died 13th of August, and he was last seen attending one of these sorts of meetings for his University Glasgow a few days before that. And when they couldn't raise him by telephone or email, they alerted the authorities in Durham, where he lived, and they had to break into his house and they found him. So he died sometime between the 13th of August and about the 10th of August. And his funeral was only last Thursday, which I attended in Durham and said a few words of appreciation for him there as well. He leaves two sisters who have the unenviable task of a house that is essentially an archive of geology. It contains samples, books, notebooks, all manner of things really that will take them and helpers like me, I think, many months to archive and distribute amongst the different people interested in what Rob did. And he also had lives where he worked on geothermal energy and environmental issues related to geology. So he collaborated in a number of different areas of our subjects, not just in quaternary and river terraces. So very sad, but I think we can have some fond memories and some memories of interesting discussions with Rob. And I'll tell you what I think his contribution was in a few minutes. I think that's enough.
Okay, thank you, Dave. Dear colleagues, let me then make say a few words on how we will work this 2 days. We have a full list of contributions, 33 presentations are in the list, and there were no cancellations still, and I hope will not be. So there will be full 2 days of listening, discussing, and I hope it will be interesting for all of us. All these presentations are grouped into three sessions according to their topics, very roughly, of course. And the first session will be devoted to methods and approaches in studying fluvial archives. There is a great variety of different methods, from mathematical modeling to geochronology, and so this is the most, I would say, the most diverse variable session. And the other two sessions are on different time scales. First is Holocene and late Quaternary, and the other is for more ancient times. Each presentation will, together with questions, will be in the time slot of 20 minutes. I'm not sure if we missed some in the presentations or we have more time, whether we should wait strictly for the beginning of another one or not. We will probably be flexible and decide it by the way. And also we will have short breaks. We call it coffee making breaks, not coffee breaks. It implies that you make your coffee and take it with you to your screens to continue our meeting. And also we'll have lunch breaks, hour and a half each day. And also to avoid the confusion with time, which is really common due to the variety of time zones, and also summertime, wintertime in the world. Please look at the program. There are now 3 columns with different time zones. First is London and Lisbon. Second is Paris, Berlin, Amsterdam, so the Central European time, and the other is the Moscow time, where also few participants are now here or in the Moscow time zone. Well, this table is European focused. I'm sorry. I apologize at our American participants. We have several presentations and participants from South America, not from North America, and it is very early now there. You can imagine it, and one of our first speakers will be Professor Barros from Brazil, who will follow Dave in some kind of an introductory session. Also, not a session, but 2 introductory presentations, also devoted to Rob Westaway. First will be given by Dave with the overview of Rob's contribution to studying fluvial archives, and Professor Barros will talk on some applications of Rob's ideas in his studies. Well, let's start our work. And well, Dave, now your presentation on the Rob Westaway's contribution to the study of fluvial archives.
Okay.
You might switch
So
to the demonstration.
I will attempt to share my screen.
Yeah.
Hopefully that's working.
Yes, fine.
And I'll put it into slideshow, or I've tried to. Now it's gone into slideshow. Yeah.
Yeah, fine.
Okay. Well, I've lost the clock, of course, by doing that. So let me just turn the bedside clock.
I will keep you informed.
It's a minute to go, so pretty good timing. This is something obviously I hadn't planned to give until fairly recently, because of the unhappy circumstances we find ourselves in relation to Rob Westaway. So that's a standard introduction with title, but also showing the various interests, and it shows the Fluvial Archives group in its original logo that I think Darryl devised, and the more recent logo that we've adopted with all sorts of fancy things on it, and also the 2 IGCP projects that we ran in the first decade or so of the Fluvial Archives, and Rob contributed quite considerably to those. That was IGCP 449, late Cenozoic, global correlation of late Cenozoic fluvial deposits, and IGC 518, something like late Cenozoic fluvial deposits in relation to landscape evolution and climate, I think it was. I didn't get the 2 titles of those quite right, but they're quite a long time ago now, running from 2000 to 2007 in sequence. Okay, well, there is the man in his element in the field, in Syria, in fact, somewhere where I worked with him quite considerably before it became impossible to go to Syria. He was a very good field geologist. You can see he has all the necessary attached to his person. He has a GPS, quite a sort of damaged looking GPS case there, or is that a camera case? No, the GPS is to the left. There's a camera case. There's a Clino compass with mirror. There's a hand lens. There's all sorts of things hanging around his neck. He was always well equipped. And in his hand, if the photo hadn't been cropped, actually, you'd be able to see a notebook on a piece of rock. And in his recent times, he was working on some pretty high-powered stuff related to geothermal energy at the University of Glasgow. And this is from one of his own talks at FLAG. He liked to put this picture of Glasgow University's magnificent buildings with the Scottish hills in the distance on his front page. But he also worked for the Open University. You can see a slightly pixelated logo from them. And he had affiliations with Newcastle University as well before Glasgow. He was a structural geologist and a hard rock geologist, really. So strange that such a person should join us studying mostly superficial fluvial deposits, but this was all about his ideas related to the crust. And I summarized them here from a paper of his in 2012 in Geomorphology. If this is going to be recorded, then you will be able to read this slide. I don't know whether you will find things like pictures intruding onto some of the text. I'll try and summarize it very quickly because I've only got a few minutes here. Effectively, the idea is that in a typical bit of a landscape, the higher points in the landscape, which is the central part in the diagram on the left, will be eroding, and the erosion will cause unloading of the brittle upper crust, which will be compensated by the mobile lower crust moving in underneath the unloaded area, which will sustain it, prevent it from sinking. And when the erosion increases, and this is something Rob recognized had happened periodically during the Quaternary with climate change and potentially sea level change as well in areas around the edges of continental crust, the erosion would be accelerated, and the process in the lower crust would also be accelerated. And that acceleration in the lower crust could actually exceed the amount of material removed by erosion, thus causing uplift that was in excess of the amount of erosion, and therefore net uplift. And because this was compensated by material moving in underneath the uplifting area, and notably unlike the uplift that we're familiar with in terms of glacial-isostasy, this uplift is not reversible. And that's the key to explaining staircases of river terraces. Whatever uplift that was that caused those river terraces hasn't been reversed. Those terraces are still high in the landscape, unlike the moving up and down of the crust in response to the melting and formation, or the formation and melting, I should really say, of ice sheets. That's the big difference. And Rob's ideas explain this, although rather than me trying to explain it to you here briefly, you're probably better off reading his own descriptions. And Rob linked this to climate change, which of course is a huge feature of the Quaternary. This is a slide from one of the important summaries of the Quaternary records of climate change from Lizicki and Ramo, 2005. And Rob sees two events in this that really can be picked out in the record of uplift as recorded by river terraces and other features. The mid-Pleistocene revolution is the most recent one, round about the boundary between the lower and middle Pleistocene, or the early and middle Pleistocene, not quite coinciding with it, but you can see it, the Bruns-Matayama magnetic reversal here, so it's slightly earlier than that. And it's when the really cold glacials kick in. So around about 22 is the first significantly cold glacial. This particular version doesn't show 22 to be as deep as some, and then 16 is significantly colder than anything that had gone before, and we know that's a big glaciation in Eastern Europe. And then 12, which is the European Elstonian Alsterian, the British Anglian. We think that's our biggest glaciation. And then 6 is another big one. And of course, 2, the last one, was pretty significant. You don't get glacials as cold as these before the mid-Pleistocene revolution. And that had a profound effect on the process that Rob described. Earlier than that, the end of the mid-Pliocene climatic optimum also caused a significant change, and you'll see that the glacials got colder. It's mostly, although there's a bit of a decline in the warmth related to this earlier change, it's the cold periods that become more severe, and with that greater severity, so the surface processes, the erosion effectively speeds up, and that speeds up the processes in the lower crust, which is why you get river terraces forming in the Pleistocene, and particularly since the beginning of the Middle Pleistocene, and you don't really see evidence of river terraces on the same scale. And the same thing really is valley incision, because river terraces are recording valley incision, and in hard rock areas, instead of terraces, you get gorges. You see those forming in those more recent times, not earlier in the pre-Quaternary record, and that's a generalization, but it's one that seems to apply in many parts of the world. The bottom graph here puts the same thing in terms of sedimentation rate, something that Rob has added here. Okay, well, an area that seems appropriate to look at, an area that we looked at following a visit of mine to that area in 2001, and I remember I was in the area when 9/11 occurred, so that's you can always remember where everyone was when that occurred. I was in Ukraine on a SEQS meeting. This is an area where you can see the effects of differential crustal type, which Rob began to explain the differences in patterns of preservation of things like river terraces and evidence for uplift that were picked up really by those IGCP projects. So the IGCP project 449 was to gather this type of data from lots of different parts of the world. And it became clear that, okay, we got nice staircases of river terraces in Northwest Europe, but we don't get them everywhere. And we'll start there with the river Dniester, which is the one to the westernmost of the 4 rivers that flow southwards across this area. The Dniester, you can see it's over here. It's very much like Western Europe. In fact, it doesn't sit on the Ukrainian shield, flowing southwards into the Black Sea, and it has a fantastic staircase of terraces. So it's just like Western Europe in a way. And in the latter part of the record, the terraces down here, this colored version up here shows all the data from biostratigraphy that has gone into piecing this record together. These terraces down here have effectively formed approximately one per Milankovitch cycle, which is something, again, that you see quite commonly in Western Europe. Earlier than that, though, terraces were forming less frequently, and they are slightly different in configuration, and you can see that they're wider. The pink ones, I suppose you'd call it, I think, a Pliocene here, and there is a Miocene basin fill that shows that before the end of the Miocene, this area wasn't actually uplifting. There was a continuous infill, but again, largely fluvial. Okay, well, you're moving to the next river eastwards, the Dnieper, you get nothing of the sort. You get a load of deposits of much the same age, and the key to the ages is here. And essentially they're side by side or on echelon, with the rivers going up and down a little bit, but staying within a few tens of meters of where the modern river is, which is here over on the left. I hope you can follow my mouse arrow when I try and point these things out. So essentially the modern river is flowing at the same level as deposition in the late Miocene. So there is no staircase here. There is no evidence of net uplift here. And Rob's explanation is that his mechanism doesn't work here because this is on the Ukrainian shield, which is essentially a craton. The crust is ancient. It is solidified fully, solidified to depth, and relatively cold in comparison with the more dynamic crust further west in Europe. And therefore there is no lower crustal compensation, and the uplift mechanism doesn't work. And I guess this is empirical evidence. This is what the record looks like. And Rob's ideas explain it. If anybody wants to say they don't believe Rob's mechanism, well, they need to be able to explain how these two rivers in this part of the world are so different. And the next river east is a slightly intermediate situation. This is the Don. This is the river where the stage 16 glaciation is so well recorded. The first real big one, according to that Lizicki and Ramo record, you'll remember. And effectively here, you've got periods of alternating uplift and accumulation of sediment or subsidence, perhaps. And you can see that in the different colors showing out different staircases. So there's an early staircase, Miocene at the top, Pliocene, and then there is a reversal, and there's accumulation of material right through until the mid-Pleistocene revolution, I guess. This is 22, and then 16, the big glaciations, and they form part of a staircase culminating in the Don Till. And then there's a staircase cut into the post-Don Till record, which has got 12 and 8, although they're in superposition. So not a downcutting event between 12 and 8. And then since 6, there's been formation of several terraces, clearly more than one per climate cycle. So pretty complicated, not fitting either the Dniester or the Dnieper pattern, but showing there's something different. This is intermediate. Rob says because this is early Proterozoic. It's not quite solidified fully, but there's a very narrow channel for some lower crustal movement to take place. I won't get into that any further. There is a river further east still. That's in case I've forgotten to. The Volga, further east still, is reckoned to be flowing onto ocean crust as it joins the Caspian basin. And again, there's no lower crustal compensation taking place in oceanic crust. So you get a stack of sedimentation in the lower Volga, and it looks something like that. And the numbers here are oxygen isotope or MIS correlations, 22 right through to the Holocene. And there are other examples. The Mississippi is a very similar example where it flows onto the Gulf of Mexico. Okay, well, these ideas came from came to interview when we both visited India and met Sheila Mishra as part of the IGCP 449 meeting in India that took place in the early noughties. And this led to a paper in which Rob's ideas about cratonic crust were expounded in conjunction with Sheila Mishra, who said to us, I've never understood this stuff about river terraces. I thought we had river terraces, but we have very ancient gravels down at river level. And the examples were in the Pravura and the Kukadi here. And this is Sheila in the field, in a field gear with one of her students, similarly attired, studying some of these gravels that they thought were early Pleistocene. But this gully runs down to the modern river. And well, Rob's explanation was immediate. Well, this is because you're on the Indian Craton, and although you've got sedimentation since and it's covered up, you've got Deccan trapped basalt, for instance, which are deeply incised. This is cratonic crust, and therefore low crustal flow compensation doesn't occur. And it came to our attention that this could also explain one of the big differences that were thought previously to be related to climate zones, which stem from the great German geomorphologist Julius Budel, who had traveled to various parts of the world and developed ideas about climatic geomorphology, ideas including, not solely, but including sort of almost a throwaway that river terraces don't really occur in the tropics. River terraces are a feature of the temperate latitudes. And well, he's right in many cases, but it's not really to do with climate. That would be our take on this. River terraces don't occur in places like the Amazon Craton, and the Amazon Craton shown here is the blue area. You'll struggle to find any evidence for river terraces in these huge areas of the Amazon. The Amazon cuts through this craton. It split it in two as a result of a failed rift arm from Atlantic rifting when the Atlantic formed. But if you go off the craton to the west, you will find that there are terraces forming in some of the headwater rivers of the Amazon, like the Acre. And Rob discovered this particular example when he visited it as part of the IGCP 449 meeting in Brazil that I couldn't attend because I was busy being exams officer for my university, which is a great annoyance to me at the time. But anyway. And Rob was the one who found some evidence that river terraces do exist in the tropics. And this example is from the river Niger in the country called Niger, or the river Niger, perhaps we in England would call it. They're not classic river terraces. They're little bits of pediment, really, tropical surfaces that seem to be fluvially molded, that seem to be in the bottom of the floodplain, preserved because the river has migrated around in the landscape and cut down in different places. One important aspect of the mechanism for forming river terraces doesn't work in the tropics, and that is that there aren't the Milankovitch cycles so extensively felt. We don't have the switch in the tropics from hugely severe cold climate to temperate climate. The change is not so big, and so the rivers are not driven by that change. But where there is uplift taking place, they will record it, as in this Niger example. And this is just showing you where that is. That's a place called Niamey. Not tropical, but southern hemisphere, the Capvel Craton in South Africa also doesn't have proper river terraces. Here, again, the rivers stayed within about 15 meters of the modern river, which is down here. That's the modern alluvium, and there are some very old gravels, early Pleistocene gravels, beneath the valley floor. So again, no terrace staircase in the Capvel Craton. This type of thinking allowed us to explain sequences in Poland when we started to look at Poland, where river terraces occur on the more recent crust in the south, such as in the Dunajec Valley and in the San Valley, as worked on by Starkel. But in central Poland, you get Pliocene gravels beneath the valley floor, infilled by you get some early incision with these Pliocene gravels forming a little staircase here, but then you get infill of more recent sediments, many of them glacial, of course, making things more complex. And Rob related this to patterns of crustal zones. I'm going to run out of time, so I'm going to speed up a little bit, which led us to draw this up in a FLAG special issue. This paper fronted by Tunca Demir, our Turkish colleague, mapping out the crustal zones and how they lead to different records of fluvial preservation. So fluvial archives differing because of different crustal zones. If you haven't seen that, that's in the journal Quaternary, the new online open access journal. And that's another take on the same thing that was published in Global and Planetary Change, a more recent FLAG special issue. This one related to the field trip to China, so really centering around ideas from the Yellow River, a paper about basin inversion, and I'll move on swiftly. Things that Rob can explain, I'll just quickly run through. We have this huge river system that's no longer there in Britain, the Bytham, which flows all the way from the southwest Midlands out across the area we call East Anglia, and its nearest modern equivalent would be the Trent, which is, you can see a line rather further north. This was the idea of Jim Rose. Jim Rose from Royal Holloway, a sometimes participant in FLAG, who thought this river up in the 1980s, and pieced together records we'd known about a long time and explained them this way. The rivers flowing out of the southern Pennines to join it still exist. So the Derby River here is the Derwent, and this one is the Dove, and they are important tributaries that are actually older than any other river flowing in this area of the English East Midlands now. One of the huge puzzles with this was that the record is in the form of gravels, and in the area to the east of Leicester, the city of Leicester, these gravels seem to form a sediment body that slopes in the wrong direction. So the sources of the rocks and the paleocurrents from faucets, cross-bedding faucets, indicate eastward flow, but the sediment body slopes westwards. Well, Rob explains this. This is the microcraton Precambrian crust in the Leicester area, reducing the uplift essentially here, so that the sediments are back tilted. End of, really, explained beautifully, and a great relief to Jim Rose, who couldn't really explain that, and it was a huge puzzle. Doesn't mean that the biotherm isn't still controversial. Phil Gibbard doesn't believe it and has suggested it really is a separate system flowing into the wash, which is where everything drains now, and nothing to do with this continuous river that Jim Rose envisages. Rob has been a vehement defender of the biotherm, and one of his last contributions was to discuss this in our own quaternary newsletters, the Quaternary Research Association's newsletter. Rob also added the cave systems of the Pennines in the Carboniferous rocks of the Pennines to the story, and modeled the caves in exactly the same way as the terraces, and made the point that the caves, which can be easily dated using uranium series methods, are telling the same story of uplift because they form in relation to valley floor level in the adjacent valleys. Another huge contribution. These are some of the diagrams he's produced from the southern Pennines.
Dave, sorry, just a slight reminder on time.
Yeah, I'll wind up now then. So I needed to put one of Rob's uplift modeling diagrams in. There's one on that area. He had a bit of a row with Dick Peltier, which it relates to the fact that Peltier's modeling, along with the Lambeck modeling of the post-glacial uplift and rebound, uses the mantle and doesn't take account of the crust. Got him into some trouble at some conferences, but I won't go through this. But there is some evidence that on modern crust, there is an important crustal element to glacial-isostasy, and some of the glacial-isostasy as a result is not reversed, which is why you do get terraces in areas on more recent crust. The famous areas where such things are modeled, like Fennoscandia and the Laurentides, they are on cratons, so the mantle explains it all. This is why it doesn't work properly when you try and do it in parts of Europe. Rob's been telling people this, they haven't really listened. There's the man in the field, always taking notes, busy scribbling there. Okay, sorry I've gone over a bit. No time for questions.
Yeah, thank you, Dave. Sorry for having to limit your very interesting talk, but if any questions, anybody wants to ask questions to Dave, we can do it in the end of the day during the discussion. Thank you, Dave, once more. We have to switch to the next speaker, who is Professor Luis Fernando Barros from Brazil. Tectonic and climatic implications of fluvial archives in the southeastern Brazilian Atlantic Plateau. Professor Barros, are you with us? I saw you in the list. Okay.
Good morning.
Morning. Very early morning for you, I suppose.
Thanks. I had some problems with my computer. I will try to share my screen with my cell phone. Can you see that? Can you see that?
Yes, we can see, but not full screen, I suppose.
And now?
Oh, good. Fine.
Okay.
Fine. Thank you.
It's now 5:47 in Brazil, AM. So good morning, everyone. And before I begin, I would kindly ask you to be patient with my English speaking. This situation is really new to me, and I might be a little sleepy still. But first of all, I would also like to record my condolences to Professor Westaway's family and friends and pay a little tribute to him. In the abstract submitted to FLAG's meeting, I make reference to a special paper of Professors Bridlin and Westaway entitled Climatically Controlled River Terrace Staircases, a Worldwide Quaternary Phenomenon. This paper was really important to me when I read it for the first time in my master course. The exposed ideas changed my mind and opened my eyes to how climate and tectonics work together in regional scales. Besides, in this paper, the professors marked the scarcity of contributions on fluvial archives from South America. So it motivated myself, and my talk today is a kind of product of this. Thus, I just would like to say thanks, Professor Westaway. And well, now I'm going to present to you the work entitled Tectonic and Climatic Implications of Fluvial Archives in the Salt System Brazil, the Brazilian Atlantic Plateau, written by me, myself, and Professor Antônio Magalhães. We are from the Department of Geography at the Federal University of Minas Gerais in Brazil. And this talk is a kind of synthesis of more than 2 decades of research by Professor Antônio and his students, including me in my master's and doctoral studies. Well, the study area was specifically the quadrilateral ferriferous domain, or literally iron quadrangle, a remarkable mountainous region with an area of more than 7,000 square kilometers, inserted in the southeastern Brazilian Atlantic Plateau. The area is drained in its western and central portions by tributaries of the São Francisco River, Paraupeba and Velhas rivers, and in its eastern portion by tributaries of the upper Doce River. The altitudes range from around 650 to 800 meters in the surrounding area, but up to 2,000 meters at peak elevations of the Caraça mountain range on the eastern edge of the domain. It is noteworthy that the highlands are supported by banded iron formations and quartzites, while the smoother relief areas are carved in gneiss and migmatites, and the intermediary compartments are modeled on schists and phyllites. The regional morphology has carved itself into Archean and Proterozoic rocks and can be defined as the result of evolution of a highly deformed geological substrate, resulting from Precambrian orogenesis. During Neogen and Quaternary, tectonic inputs led to intense dissection through drainage of ancient planation surfaces. But in this process, a strong structural control induced the inversion of the relief, leaving relatively topographically elevated synclines and lowered inclines. So there has been a predominant role of fluvial work in shaping the landscape in the region. Then several surveys on fluvial terraces and its depositional successions have been undertaken during the last decades. About the methods, we made an extensive literature review in regard to fluvial archives, and the study sites were identified and revisited to review and reinterpret the data in the field and in the regional setting. 13 valleys were investigated, covering the main valleys in terms of preserved fluvial archives. In each valley, the predominant means of identifying different fluvial levels were the heights and characteristics of the sediments of which they were composed. And the depositional levels, floodplains and terraces, of all valleys were separated into regional phases of fluvial evolution, based on the relationship among data from the depositional successions, such as the presence of dirt grass, geomorphological context of each level in its respective valley, it is its relationship with older or younger levels, and sediment age when available. Well, the framework of fluvial levels in each valley allowed us to propose 7 regional phases of formation of fluvial deposition levels between 83,000 years and the present. In this image, we have the studied river valleys and the respective profiles of the depositional levels. They vary a lot in relation to each other, but in general, the valleys of the Paraupeba River catchment and the Doce River catchment have a greater number of records of old fluvial depositional levels. And it is noteworthy the presence of staggered terraces throughout the area. Here we have a summary of the dating results considered in our analysis. They come from a lot of studies, but all were obtained by optically stimulated luminescence with MAR and primarily SAR protocols. In turn, here we have a stratigraphic model which represents all of the fluvial archives relative to each regional phase. And the mean age of each phase is also indicated. I would like to highlight the presence of thick conglomeratic dirt crusts in the fluvial archives of phases 2 and 4. Well, there are a number of evidence regarding tectonic influence on the evolution of the river valleys, such as trapped tectonic sediments and the formation and failure of sedimentary deposits. Here, on left, we have the abrupt river diversions and location of probably sediment traps along the middle Conceição River Valley, indicating strong structural and new tectonic conditioning on the fluvial dynamic. On the right, a normal fault in the middle terrace of Velhas River with offset of 1.5 meters. Unfortunately, a lot of important fluvial archives like these were destroyed by human activities, so we could not take recent photos of them. But the widespread presence of terraces staircases in the valleys can be considered, in general, a responsive phase of greater fluvial incision. But the consecutive formation of river bedrock terraces is commonly attributed to regional uplifts. However, in this case, each fluvial dissection phase is unlikely to correspond to a different new tectonic pulse, as there is no evidence in the literature of such a large number of different pulses during the last 100,000 years. But there are proposals of correspondence of new tectonic pulses on the Brazilian platform with Andean orogenic events, being the final pulse in the lower to middle Pleistocene. So this event would have been responsible for a generalized uplifting of the Brazilian platform and can be related as responsible of an intense process of fluvial incision in the region. It is also noteworthy the high fluvial incision values found, even in the Holocene. The data suggests that Paraupeba catchment is draining a tectonic block that had greater uplifting during the late Quaternary. Incision rates in this catchment can reach more than 2,000 millimeters in 1,000 years, values close to those of orogenic environments. However, it is crucial to point out that in no case was the outcrop of hard rocks observed to be below the river archives, and they were always on saprolite. Thus, it appears that the incision on the saprolite would explain the high river incision values, highlighting the importance of valley bottom weather processes. This image illustrates this common occurrence. We have a synthetic stratigraphic profile and a representative image of the fluvial archives corresponding to phase 3, about 36,000 years, in Maracujá River Valley, one of the less dissected ones, above about 2 meters of exposed benign saprolite. We also noted the occurrence of conglomeratic dirt crust in the riverbeds, influencing the incision rates. For example, phase 2 records, about 47,000 years, are at a height of 60 to 80 meters above riverbed in the Paraopeba Valley, while in the Conceição Valley, deposits are at 15 to 20 meters above riverbed. In the former valley, there are basically no conglomeratic dirt crusts, whereas in the later valley, they were formed recurrently. Dirt crust of phase 4, with approximately 26,000 years, are also present in several other valleys bottoms: Conceição, Caraça, Barão de Cocais, Mango, and Maracujá, and may have prevented the waterways from experiencing a later fluvial incision phase, being the youngest fluvial successions nested in phase 4 deposits. Here we have the micromorphological aspect of the conglomerated dirt crusts, and the ferruginous cement has different organizations: micronodular, coatings, or infillings of the secondary porosity. It was formed by the precipitation of iron oxyhydroxides due to the oscillation of the water table, enriched with dissolved iron, in thick and coarse fluvial deposits. The image also brings microchemical maps of some elements, of which I highlight iron, which is evident in both class of banded iron formation and cement. Another important question to note is a clear alternation between fluvial phases developed in a moister and or warmer climate in phases in drier and or cooler periods, according with literature data. The average interval between the moister, warmer phase is approximately 41,000 years, while that between the drier, cooler phase varies between 21 and 18,000 years. Thus, the interval between the moister, warmer phase approaches that of the Earth's obliquity variation cycles, whereas those between the drier, cooler phase approach the Earth's cycles of precession of the equinoxes. However, it would be reckless to invoke the mechanism of crustal loading and unloading proposed by Professors Bridlin and Westaway to explain this pattern of the Earth's observed, because the existence of several fluvial levels within the same 100,000 year cycle is considered unusual. So it seems to us that the valley bottoms were filled in the dry phases, related to thicker successions and conglomerated dirt crusts. There would have been no river dowel cutting in bedrock. In the wet phases, a relatively quick fluvial incision occurred, first in the previous accumulated sediments, and in the following context in the saprolite, leaving staggered the dry phase records. If fluvial incision occurred in a certain balance with sedimentation, then fluvial successions during the wet phase would be accumulated. However, due to the permanence of the incision, there would be a migration of nick points and consequent abandonment of the wet phase records. And the return of a dry phase would start a new cycle. This is a model proposed by us for the geomorphological evolution of the Conceição and Mango River valleys, influenced by vegetation dynamics in response to climate variations according with phytolytes analysis. However, it could be applied to the general understanding of the fluvial history in the region. And as conclusions, we must point out that the studies with absolute dating techniques in the region are still in a process of building up data resolution and data density. Thus, we present a first attempt of synthesis, which can be reevaluated in the future. But it is clear to us that the regional fluvial archives indicate a dynamic and young fluvial landscape, sensitive to tectonic forces and climatic oscillations of the late Quaternary. Probably a new tectonic pulse in the lower to middle Pleistocene would have been responsible for a generalized and intense process of fluvial incision in the region. However, it would have occurred in phases, accelerated to a greater or lesser extent, according to the variable conditions of sediment production and outflow in the valleys. And this fluvial incision occurring in high rates due to intense weathering process in the valley bottoms. In other words, it was done in weakened saprolites. Well, that's all. Thank you for your attention.
Thank you much, Professor Barros, for your interesting talk and for your keeping time. And we probably have time for a couple of very short questions if we need. To ask questions, please raise your electronic hand in the lower right corner of your participation screen. Okay, thank you much and have a good trip. I know that you are leaving somewhere in a while. Let's switch to the first regular session, methods and approaches for studies of fluvial archives. And let me to convene this session and first to check if all speakers are here. I see everybody except for Mihai Aksamit. Mihai, can you show yourself? Okay, probably Mr. Aksamit is not with us, so we have another 20 minutes for other speakers. And the first one is Mrs. Ilona Tomczyk-Widysz.
Yes, okay. Thank you. Good morning.
Morning. Let me introduce your talk. Bottom sediments as an archive of anthropopressure. Case study from Kielce Upland, Poland. Take your time, please.
Do you see my presentation?
Yes, quite fine.
Good morning. My name is Ilona Tomczyk-Wydrych. I am a student of doctoral school. My field of study is earth science. I am at the beginning of my scientific adventure. And today I'm going to give a presentation about bottom sediments as an achieve of anthropopressure case study Kielce Upland in Poland. The subject of the presentation is part of my doctoral dissertation about the functioning of aquatic ecosystems under condition of varied anthropopressure of the example of the Kielce Upland. Today, I will present the research areas, methods, and expect results, but the results will be soon. The accumulation of bottom sediments is a process characteristic of all types of water reservoirs. The course of this phenomenon and thus the composition of bottom sediments depends on many factors. For example, the geological structure of the catchment, the type of soil, the morphology of the catchment area, and the size of reservoirs, and of course, about degree of catchment development. In non-industrialist area, the composition of bottom sediments, including the content of trace metal, depends mainly on the lithology of a given catchment area and the climatic condition. But the enrichment of the reservoir sediments with trace metal observed in industrialist area is mainly the results of human activity. For example, emission of pollution into the atmosphere, with a result of wet deposition and surface runoff get into surface waters. But regardless on the surface type, trace metal migration to the waters are mainly deposition in bottom sediments. Therefore, bottom sediments are an indicator of the ecological condition, not only of reservoir, but also of the catchment area, playing the role of a specific integral indicator of the level of anthropopressure. The main goal of the study is to determine the impact of anthropopressure on the geochemical diversity of bottom sediments. The specific goals are determine on the physical and chemical properties of bottom sediments, determine of trace metal concentration if bottom sediments, and determine of factors influencing the quality of bottom sediments. The investigations concern 3 water reservoirs, Borków, Wilków, and Rejów, located in the Kielce upland. The reservoirs are multi-purpose. They perform a retention, recreational, and tourist function, but they differ in age, capacity, and size of the catchment area, and of course, land development. The Borków Reservoir was built in 1976 on the Belnianka River. The reservoir has an area of 36 hectares and a maximum depth of 3 meters. Above the reservoir in Belnianka catchment area, there are point sources of pollution. For example, sewage treatment plants in Daleszyce and Bieliny. There are holiday centers operating mainly in the summer season near the reservoir. Wilków Reservoir formed on the watercourse from Święta Katarzyna. It was put into operation in 2004. The damming element is an earth dam with a length of 390 meters. The use of the catchment area is evenly disturbed between forest management and agriculture. The remaining area are occupied by permanent grassland, loose housing, and industrial or commercial zones. The Rejów Reservoir was built at the beginning of the 19th century. It was destroyed during military operation during the First World War. Then in 1925, it was rebuilt again and then destroyed in 1939. After Second World War, it was rebuilt in order to meet the water needs of Zakłady Metalowe Mesko. The reservoir fills up the water of the Kamionka River with the help on an earth dam. The Kamionka River flows through the central part of the old Polish industrial district. Forges and water mills operated in this area from the Middle Age to the end of the 19th century. Until today, there are remains of industrial activities, including metallurgical plants and mills. The bottom sediments will be collected in 2021 and 2022. Samples of bottom sediments will be collected from surface layer using a tabular scope and a sediment course in quasi-undisturbed state, with the structure and layer thickness preserved into transparent cylinders using a Becker sample. The obtained material will be analyzed in terms of grain by CF and laser method and pH. After mineralization, total content of trace metal, for example, cadmium, lead, zinc, chromium, will be analyzed using the mass spectrometry. And based on this data, sedimentation, pH, geochemical maps will be complete. Bottom sediments are an excellent indicator of the influence of the catchment area on the ecosystem of the reservoir and also reflect its ecological condition. The selected water reservoirs differ from each other, for example, age, area, and the way of managing the catchment area. This suggests that the content of trace metal in bottom sediments will be vary. This may be the result of the anthropogenic pressure, cause the impact of industry, agricultural activity, sewage discharge from sewage treatment plants, and runoff from road infrastructure. Therefore, in this study, I focus on determining the factors that may affect the content of trace metal in bottom sediments. The results of the research can be used to determine the current state of the environmental intensity and scale of the impact of natural and anthropogenic factors on the ecosystem. I think it is particularly important from the point of view of environmental monitoring, especially issues related to water protection. And the results will be soon. Thank you for your attention.
Thank you much. And we have a lot of time for questions. Please, colleagues, raise your hands. Oh, sorry. Excuse me. Please, Hans.
Yeah, thank you very much for this nice talk. I think this will be a very interesting study. I just have a question. Maybe I did not get the point. Do you also plan to take samples from the catchment areas and not just from the reservoir sediments? Because I could imagine theoretically that you could have a change in the contribution of different heavy metals just by a change of the lithology. So I could imagine that, for instance, after erosion of possibly a loess cover in the catchments, you will get a totally different geology, so that such a change maybe occurred during the last decades, and that has nothing to do with anthropogenic activity.
Thank you for your comment, but can you repeat your question?
Yes, my question is, maybe I missed the point, but do you also plan to take systematically samples in the catchments of your reservoirs? Because I could imagine that maybe after erosion of a superficial loess cover or periglacial cover bed, you enter with erosion into bedrock so that you get a strong geochemical change without any change of anthropogenic pollution. It's just a geological change. You understand what I mean?
Yes, I understand. But my research are at the beginning, and I think I must wondering about this geological.
Yes, so it's okay. I understand. It's just a suggestion for you at the start of your research.
Yes,
also
yes,
to think about this issue, that in the end you don't interpret something that has nothing to do with direct human input of heavy metals. But so that's just a suggestion for you. But generally, I like your study, and I think it's really exciting to look at.
Okay, thank you very much for your comment.
Thank you.
Thank you, Hans. Colleagues, other questions to Ilona? Okay, no questions, probably during the discussion in the end of the day.
Okay.
Thank you, Ilona.
Thank you.
And we can switch to another speaker. Pyrotrepiora, macro and microscopic slags as a marker of the metallurgical activity in the Holy Cross Mountains. Please,
Yes.
Paweł.
Hello. I hope everyone hear me. Yes.
Yeah. And you have additional time, so.
Yes. One moment. I'll prepare the share screen. I hope everything is fine. And do you see it?
Yes, fine.
Yes, there is no problem here. Okay. Somehow this. Oh, okay. This will not need it. All right. So thank you very much. I represent the scientific team from the University of Jan Kochanowski in Kielce. And with the scientific team, with our scientific team is also the scientists from the University of Liège. Together we prepared a presentation about the macro and microscopic slags as a marker of the metallurgical activity in the Holy Cross Mountains in Poland. Short information, what is the macro, microscopic slags and magnetic spherules? As we can see on the picture, the slags are the post-industrial remnants in the sediments. They are different size. The bigger one, a few in bigger centimeter slags, smaller one showing in the picture looking like sometimes some like iron balls, and the smallest, the as we call magnetic spherules in the micrometers size, are the very good indicators showing us the increase of the anthropopressure biometallurgical activity in the fluvial environment. The most important is the microscopic iron spherules. That size is 220 to 63 micrometers. So only way to find them out is to watch them under the microscope. We can see the sample, one of the sample here. The closer look to them, we can find some kind of elements looking like they're perfectly spherical elements. They are not natural, they're empty inside, and they're how their origin is. They're created during the metallurgical activity of the forges or even other iron works in the fact. How we separate them? We know that those materials are anthropogenic. They are different type than natural ferromagnetic material, but the all sample have many ferromagnetic elements that we separate during the sieves and the magnetic ripples. Then we take this material under the microscope and manually count how many of them there are. The iron spherogenesis is very interesting because the Dunward and Wilkes show us the welding experiment that shows that under the hammer impact, there is many microscopic elements separating from the iron, the hide iron. They're called the hammer scales, and mostly the flaky are the spherical product. The spherical product is perfect rounded elements that we can see on the microscope, and better to separate them from the natural elements in the sample. They are empty inside, looks like the bubble of the iron, and that's why they can be transported even the few kilometers from the origin, that means from the forge, and accumulate and sometimes redeposited by the fluvial activity. And this is the first time when we use this method in the Eastern Europe, in the central Poland. This is the study area, the central Poland, the northern part of the Świętokrzyskie Voivodeship. We selected 5 sites where we use this method in the first time. This area is located on the geological structure, mostly in the Mesozoic margin of the Holy Cross Mountains. The geology is very important because there was many iron ore deposits here, and in the historical time there was the old Polish industrial district area. So we can see on the map this study areas is located on the central part and of it, and some of them are located on the prehistoric in Roman Peroid metallurgy area, the first one site, and the rest one are located in the later medieval and modern old Polish industrial district. We can see the forges located on the rivers, the black spot, and the Blue Mary's area. That means the prehistorical time period of metallurgy. So showing the sites from the chronological, the first one is located in the Dołe Biskupie site in the Świślina Valley. This area was known from the prehistorical metallurgy activity. We have here our own profile made on the floodplain and a historical profile made by the Klatka from the 1958. It is very important because the first time he showed us that in this section there was many remnants of the anthropogenical activity of metallurgy here. So we have the charcoals, and even deeper, he found the slags and iron ore. The bigger slags he found here, he proposed they are in situ, and perhaps they are connected with the prehistorical or even medieval metallurgical activity in this area. Why he say this? Because this catchment of the Świślina is very important for the prehistoric metallurgy activity. We can see there's many exminate Blue Mary order and disordered type styles located in the upper part of the catchment, and the interpretation of the Blue Mary slag site shows that very many of the slags accumulation in this area, and the study area is located in the downstream of the Świślina. So there is also some of the Blue Mary slag sites there, but not so many as in the upper part. So probably, of course, before the water reservoir in the central part was built, perhaps those slags was redeposited in our study area. And the only new one remains of the modern metallurgical activity is located in the estuary of the Świślina do the Kamienna river. And this is the only one remnant of the 19th century sheet metal factory in Nietulisko, but this is only a short information, and we not connecting these slags with this with this modern metallurgy. Our profile made in the floodplain show us the lithology that we have some kind of very well visible flood layer. Beneath this flood layer, we have seen the carbonate and pH become lower. But most interesting that geochemical analysis of the selected heavy metals show us that they become increased beneath that flood sediment layer. We can see it very well on the lead, zincum, and of course the iron. But why this heavy metals become increased? We can connect it maybe with this method we used with microscopic spheral separation, because we found only in the sediments beneath that layer many metallurgy traces as the spherules accumulated in here. Why they are accumulated only in the upper part of the profile? Perhaps, as I said before, they are probably redeposited and they are traces of the perhaps the prehistorical metallurgy activity in the upper part of the catchment area. The younger metallurgy, older metallurgy, that means the medieval and modern. For example, in the Zakole site, we made a profile in the Oxbow Lake and the overbank sediments near the Czarna Konecka. And here it is. Again, we got same situation, some sort of the iron balls, as we call them, are accumulated into two phases of the Oxbow Lake. Probably it shows us that it's again redeposited, because it shows us that this Oxbow Lake was again used by the river at least 2 times and accumulate redeposited material from the nearby forges. And the most important is the overbark sediments, showing us that we have some sort of the iron balls accumulated on the entire profile. But we have here very increased accumulation of them in the one layer. Probably it's showing us the probable metallurgical activity level of the floodplain from the moment of the last time when the forge nearby was activated. Also very interesting situation is the third side, the Jędrów side. We can see the modern metallurgy was also very well seen on the digital elevation model. Now in the place of the old forge is located a water mill, but still we can see the very well visible hydrotechnical infrastructure. We made the cross section downstream from this infrastructure from the entire floodplain area, and we can see the lithological increase of this material accumulation in the lower floodplain, in the upper floodplain, and Pleistocene terrace. And important is that we found very intensive slag deposits in the upper floodplain. The macro slags concentration show us that we have in the upper floodplain slag deposition, and some of the slags accumulated in the lower part of the profiles in the level where we have the gravels. And we don't found any slags closer to the river. The microscopic slags deposition, that means the iron balls, show us different situation. We got most of the iron balls accumulated only the lower floodplain area in here. So we concentrate our work on the floodplain. We can see the lower floodplain lithology, how the macroscopic slags accumulated only in the bottom of the sediments, and some of them are deposited from the upper floodplain from these deposits in GRK4 profile. But most important is that in the entire level of the floodplain, lower floodplain, there we found many microscopic slags. That means they are mostly the magnetic spherules. And important is that they're creating some sort of the post-industrial sediments layer. And again, we can say that probably this is the level of the last time when the floodplain was, this is the level of the probably of the floodplain of the last operation of the metallurgical activity in this area. That means the forge nearby in the Jędrów, in this site. Also on the same river, we made such a first time an analysis of the microscopic slags on the sediments from the of the lake sediments. In this fact, we got a situation when the Suchedniów reservoir will become dry after hydrotechnical works. We know this area was built, this reservoir was built on the area where was historical industrial reservoir near the forge. And we can see the very well visible three layers of the sediments. The first one, the historical deposits of the lacustrine, the black one, and we got the mega ripples from the flash flood deposits during this flash flood was during the building of the new reservoir, and the modern lacustrine deposits. And important is in the three of those sediments layers, we got iron balls selected in this separated from this sediments. The first one we can date for turn of the 19th century, when the last time this lacustrine sediment was accumulated during the forge was working here with this reservoir. The second one is known from the 1974 when the flash flood was become, and probably those iron spherules was become to redeposited from the upper part of the catchment, where also there was a few iron works operating from the last century. And same situation is with the modern lacustrine deposits, also redeposition of the in the later times, in the later maybe floods, accumulation of the iron balls in the sedimentation basin as a new reservoir in here. And the younger situation with another reservoir also located in the place where there was a post-industrial area from the old forges in the Czarna Konecka. Also, the reservoir became dry after hydrotechnical works. So we entered there to prepare our work. We found there also the black oaks under the lacustrine sediment that's showing us the different different environmental changes after the medieval metallurgical activity become, but I will show this maybe with the next presentation. This will be more shortly here. Important is that we have here two layers: lacustrine deposits, we can see in the picture, and delta deposits built mainly with the slags that creating some kind of deflation pavement on the top. We made a cross section showing us in the lithology perhaps at least three different phases of accumulation of the sediments of delta. But important is that we try to separate the spherules, ferromagnetic spherules from the sediments. There was not so many of them, only one, maybe two or three per sample. But it showed us somehow a very interesting fact that those spherules accumulated mostly during the second phase of the creating of this delta. Maybe the flow was become lower, and most of them supposed to be accumulated in the bottom of the lacustrine sediments. So again, we have some kind of accumulation in the accumulation basin as the reservoir, and so we have more spherules accumulated in the lacustrine sediments. Short conclusions about this method. We know that magnetic spherule separation method with a similar effectiveness as well was made in the Wallonia area in the Belgium. It can be used in other sites of the Central and Eastern Europe where the prehistoric and historical metallurgical activities was developed. The slightly modified method can be used as so far in the floodplain area, but also effectively in deposits of different genesis. So we have the flash flood secular and lacustrine sediments in fact shown here. And this method can be used in detected the prehistorical, that means bloomeries, and medieval and modern, so-called forges and blast furnace metallurgical activity in different types of deposit and show its accumulation rate and able to dating them, of course, using also the historical materials. The macro and microscopic slags with also the spherules are good markers showing the metallurgical activity in the old Polish industrial district river valleys, only in situ and redeposited sediments as well. Thank you for your attention.
Thank you, Dr. Przepiora. Dear colleagues, please, your questions. I have one. As far as I understood, you use this method, the remains of the metallurgical slugs, to demonstrate the presence of metallurgical activity in the catchment of the river. So you can date the alluvia where you have found the slugs, and then to say that, okay, at that time the metallurgy was occurred here or in the area. Can you use these methods in the opposite way? I mean, as a stratigraphic marker or even chronostratigraphic marker? Can you date the slugs and use them to date the alluvial sediments?
Okay, thank you for your question. Yes, so from the beginning, I was try to show that using the historical materials, of course, and different methods of datings, maybe in future with the OSL or thermoluminescence dating of the material, we can try to date these layers where we found this artifact. So we can connect this, of course, with the historical data. That means the materials that showing us when the last time the forge was working here, operating here. The worst situation was with the prehistorical. We don't have data about this. Only way is to date the material of the sediments and then try to connect it with this artifact in the sediments. It gives us information in the progress of the accumulation of this material, or it shows us that perhaps this material is not in situ or deposited. It shows especially with the younger material in delta. We know where the delta was accumulated, so there is no chance that this material is in situ. It was transported from the upper part of the river. With the prehistorical material, the problem is that it have to be this supposed to be science. This science supposed to be interdisciplinary with the historian and archaeologists who know how to separate and show what kind of slags supposed to be looks like from this prehistorical time. There was a different method of the metallurgical activity. There was different slags created from the bloomeries, and they know how to find them and decrease from this modern times when the higher level of technology give us a chance to create more slags, and those slags looks different. So this gives us also information how to dating these sediments, and show maybe the sequences of the accumulation of different type of the river. Of course, this is the preliminary results showing us from few different sites. We try to do maybe to test this method, maybe here, and we give very interesting materials to show here now in this presentation. So I hope there will be more materials from different sites. We select them to proceed to the next stages of our work. Just like I show you maybe from the Jędrów site, where we have the cross section, very similar made like our friend from the Belgium making from the flat plains, showing us the level of the perhaps the old flat plain from the time when the last time was operating the forge in this area. I hope it will be in progress. I hope so. There will be more material in the future.
Thank you much. Pedro, please, your question.
Hi, nice presentation. I have only two short questions or comments. First is how we can evaluate the recycling of the slags of these materials. And also, I think these materials, because anthropic materials, because they are quite dense, they will be more accumulated together with coarse materials, for example, with sand and with gravels. So we get a wrong idea of intensity of the metallurgical activities. So how can we discriminate this?
Thank you for your question. So the macroscopic slags, of course, that more than centimeter and bigger slags, of course, they have to be transported by the fluvial activity of the river, or maybe they are in situ, just like the older materials from the Świślina River, so showed by Klatka. He found there bigger slags, bigger than 20 centimeters even, so perhaps he say that it's supposed to be in situ somehow, but it don't have to be. Yes, this everything it shows us that the coarse material can be transported during the flats. Yes, during the flash floods, maybe it's deposited. With the microscopic slags, just like the microscopic spherules, they are so small, they are mostly transported in the beginning by the aeolian transport. So we know that it can be transported even for 10 kilometers from the origin, and then accumulate in the sediments and cover with the sediments in the alluvia, or even sometimes redeposited with the sediments. They are flushed out from this area, and that's why perhaps just like in the delta we showed, those spherules was not so many. They are flushed out, there are not so many, but they are redeposited and transported and accumulated again in the younger form, in the younger sediments. So this gave us some information how to interpret the existence of this small artifacts in the sediments. That's why we're trying to do now on the Old Polish Industrial District area, where we have the prehistorical time, medieval and modern time metallurgical activity. So there's very many information and historical and archaeological data from this area, so we can connect it somehow.
Thank you. Pedro, your second question? That's all. Fine. Hans?
Yes, I have a very short question to you. When we talk about the microslags, what do you think about their preservation potential in oxidizing environments? For instance, I'm thinking about microslags from the Iron Age period, maybe 2,000, 3,000 years ago. Do you think that these can be well preserved, however, in oxidizing floodplains, for instance, after incision? Is there anything known about this?
Truly, I don't know if they were well preserved. I'm still before the connection with the archaeologists who working on the bloomeries in this area, where you know. Before I was talking with him years ago, he's showing me how the slags looking like before the medieval and the modern times. The medieval, they are looking more like with more bubbles inside, yes, because this is we insert much more oxidite into the forges, the better technology of this. In the bloomeries, they are looking like, how to say, like simple forge with no infrastructure. So they're using the blow of the wind, sometimes with their own hands. The temperature was a bit lower and they're getting less iron from the iron ore. So they're creating much more slags, creating bigger slags, of course. But those slags have much less oxidate and technology was worse. Of course, near the bloomeries, they're also working the hammer sites, so they also creating this kind of microscopic elements like iron balls in this fact. But this need more data. We're trying to get some the site where this bloomeries was operating, make the profile and get again this kind of microscopic elements from the sediments and try to date these sediments by maybe OSL dating. So give us more information if truly this is the moment when the last time was operating the prehistorical metallurgy in this area, or even this is the younger from the other sites. But maybe I will show this in the next presentation, because I know that my colleague Michał Aksamit will be after me, but he cannot connect it. And we're showing the next stage of this kind of work we're doing here.
Just to come very shortly to the main issue of my question, do you see any post-sedimentary destruction of those slags, and for instance in the medieval layers, that you see, okay, maybe this starts to dissolve due to oxidation, that maybe the signal is lost after 2,000 years? Do you have indications for this?
Probably the signal is lost, but maybe we need to use different methods to try to find this. Yes, just like I say, this is the first time we use this method, and we're still operating on this area, trying to connect it with the different ages. Yes.
Yeah. Thank you very much. Very exciting study.
Thank you.
Yeah. Any other questions? Pavel, I have a question to you.
Okay.
About your colleague Michał Aksamit. Will he present or not?
Yes, but I see my colleague sent me information that you call him already, but I saw that he's supposed to present after me. Yes.
Yes, but I have not found him in the list.
Yes, because he cannot connect it today, so he told to me that I will present here this matter.
Okay, so you will change him.
Yes, I will. I am prepared.
Okay, good. Let's switch to your other talk.
Okay, so the next presentation. Give me a moment. Okay. Share the screen. I hope you will see it. I hope you see the screen.
Yeah,
yes.
Yeah, we see.
Okay, so the this presentation connected with the last presentation. Again, we have the scientific team with the University of Jan Kochanowski and Liège University, and this time I concentrate. our work with the macro and micro slags in the delta deposits of the post-industrial water reservoir in Sielpia. So I will show much more information from this stage. So this study area is located in the central Poland, in the northwestern part of the Świętokrzyskie Voivodeship. This is again the Mesozoic margin of the Holy Cross Mountains. And important is that this area is located in the central part of the Old Polish Industrial District, where we have the many forges from the medieval and modern period located on the rivers. We can see the black spots connected with the rivers, showing that's the forges in this area. And the Czarna Konecka River is the one of the most important river, most of the working rivers on the Old Polish Industrial District. As we can see, there is the much bigger concentration of the forges, especially in the central and the upper part of the Czarna Konecka River. Short history of the reservoir we shown. There's important because this reservoir in the beginning become an industrial pond from the Niba Forge and iron works. Later, in the turn of the 19th, 20th century, it was no longer used and destroyed, and there was drainage, there was a dam break, the flood, again rebuilt, and again flood, and again rebuilt. So there was many catastrophical events on the river that lead to destroy this reservoir and rebuild it later by the human. But important is that last years that we have drainage the reservoir for the renovation of the dam in 2011, and the beginning of the revitalization, the silting of the reservoir in 2018 that give us chance to enter to the bottom of the reservoir and start our research. The other researchers also concentrate on this area on the other kind of remnants of the Old Polish Industrial District. This kind of charcoals. In this fact, the charcoal kilns was found in the digital elevation model, showing us many of these kind of structures around the Sielpia reservoir. What is the charcoal kilns? They are built in the places where there was woods. They creating charcoals from this kilns to fuel up the nearby forges. This reservoir is located in the downstream from the other industrial ponds that operating or was operating in the upper part of the Czarna Konecka River. As I said before, there was a many flash flood in the anthropogenic small water retention system. In the last years, there was many of this kind of events, creating some kind of, we can say, erosion zone where the material during the flash floods was erode and transport and accumulate in the accumulation zone. That means in the reservoir in Sielpia, lead to create the inland delta. This is the picture from the 2000, first showing us the scale of this inland delta. Sometimes we can tell this is not the inland delta, but high energy subaqueous fan. This is the 2 years later, showing us another progress of this form after another flood, showing us how many material was redeposited from the upper parts of this river. And again, we can see the progress of this delta, the silting of this reservoir, and again in 2018-19 there was starting the hydrotechnical structure rebuild and the silting, but still we have the visible delta under the water level. That means the subaqueous fan. Why the hydrotechnical works started? Because the Sielpia water reservoir become very small. The capacity of decrease about 60% from the 1974. From 1974 for over 60%. It was about 5 hectares, and you can see the average depth is about 10 to 60 centimeters in the estuary of the river to the reservoir. So this is how this reservoir looks like after the hydrotechnical work started. We entered to the bottom of the reservoir and we found many black oaks here. We dated them by the dendrochronological method and radiocarbon method. And this dating should give us very important information that every of those subfossil trees was fall to the sediments before the medieval and modern iron ore mining and metallurgy was started activity in the Old Polish Industrial District. So we have seen that maybe this charcoal kilns, what was working here in the medieval, lead to change the deforestation of this area. And we have probably the marker of the natural fluvial processes in this area before the reservoir was built in here, well, before the metallurgical activity was started. I hope it's, yes. And the most important is the delta. We made here the cross section. We can see the visible on the top of the delta ripple marks created by the sand and gravels. Just like say before, we have the delta deposits covered with the slags, creating some kind of deflation pavement. Those macroscopic slags are many of them here, and lacustrine deposits from the reservoir that the modern reservoir is working now. And just like before, we're showing the microscopic slags, how there was redeposited in here. So we have three very well visible lithological phases of accumulation of the delta. It shows us that most of the red silty sands with gravels and gravels on the red, showing us probably there most of them are the slags with the macro slags redeposited, but microscopic slags, the spherules, there's not so many of them. They're supposed to be flushed out from the upper part during those flash floods I showing you before, and during another accumulation of the sediments and building this subaquifan or delta in the last years. And they accumulate during the second phase, mostly in the second phase. Maybe this is too much to say that they accumulate in the second phase, because we found here only one spherule per in the sample. But we're trying to interpret this as the accumulation between two phases of the floods in the first and third stage. And most of the spherules supposed to accumulate in the bottom of the reservoir. So it's same is in here in this situation. Those spherules a bit more are accumulated in the sediments, in the lacustrine sediments. There are less in the delta sediments. So we have here the accumulation basin here for this kind of for these microscopic slags. And small conclusion that we have here, that there is many small reservoir upstream of Shelpia that was abandoned and destroyed during the floods, and lead to showing the Shelpia reservoir and creating the large inland delta in the short period of time. The iron spherules detecting the delta sediments of the Shelpia reservoir can be, of course, connected with the secondary accumulation phase, but it has to be some kind of flash flood during daybreak or smaller reservoir upstream in Czarna-Konecka river. The macro and micro slags preserved in the delta sediments was flushed out from the upper section of the Czarna-Konecka. They cannot be operated here because this is younger material. And those slags supposed to be connected with some kind of forges were operating with similar industrial ponds in the upstream. That means creating, as we know, anthropogenic small water retention system on the river. And the obtained results indicate that magnetic spherule separation method has been used so far mainly in the flat plains. It can also be effectively used in the sediments filling the bottom of the former industrial ponds, including, of course, the younger inland deltas. And thank you for your attention. This is how our students working on the bottom of the reservoir.
Thank you
very much.
Thank you much. Colleagues, I was said that Dr. Andrzej Kirchner wanted to ask a question. Sorry, I haven't noticed it. Please, Dr. Kirchner, you may ask it, okay?
Okay, so yeah, now my video is running. All actually, I have a question to the entire project. Have you thought about these cross sections in different parts of the catchment, like in the upper, in the middle, or in the lower part? Because I can imagine that next to the vertical distribution, then we can have an idea on how the slacks actually, how long actually the slacks needed to travel once through a catchment. And so next to the vertical idea, we can get a temporal idea of how long this actually needs. And therefore, I'm not so sure if we can talk about the first, second, and third phase if we are in different areas of the catchment. So, have you maybe included this idea in your project already?
Thank you for the question. Yes, this is a very good idea to make the cross-section from the entire catchment maybe, but I'm showing the presentation with materials from the different works of our students, my own. They're in progress or they stay in the place now in this situation. The cross-section is made in the only 4 profiles, and this is the first stage to try to use this method on the younger sediments. We just say, hey, let's try to do this on the sediments from the delta. And well, we got some kind of material here. And this gives us only information to try out to make more this kind of analysis maybe in the upper part of the river. Just like in the presentation before, I showed there is a site with the Oxbow Lake. Yes, this is the upper part of the Czarna Konecka. This is the same river upstream from the Sielpia River. And there is much more of this kind of microscopic slacks. So this gives us a point to do this kind of cross-section, showing us how this accumulation of these microslags are changing during the entire river length. Maybe not the entire river, maybe to this Sielpia reservoir, because the sedimentation basin mostly stop the sedimentation, the fluvial, in the next stage of the river. Yes, so we don't know how this will work, but we know there is many forges. As I say, they can be transported by aeolian and redeposited and transported by the fluvial activity. This gives us only the only point where to start our work. Yes.
Yes.
I will try to do this. Just the cross section in the Kamionka we made with the flat plane, but across the entire river. Yes, this is a very good idea, but we need more profiles.
Of course, it's rather a suggestion, but that is something we observed when we looked to like heavy metals in an industrial areas here in Germany. Then we could see that near to the source area, of course, this input is rather early, and if we are going to the mouth of the river in the lower section, then the signal just arrives like 500 years later. So it is just a nice way to figure out how long slags actually are in the floodplain and how long they need to come from a sink, from a source to a sink. So this is rather a suggestion. Thank you.
Yes, but we need more datings. Yes,
of course, yeah.
OSL or the TL datings of the sediments, but of course, in this situation, we got also the subfossil trees, trunks that we can dating and give us some information that they fall before the meteorological activity was started. Historical data show us that there was no meteorological activity before the medieval times in this area.
Okay.
So this gives us a point, yes, to date this kind of materials. Thank you. Thank you.
Thank you.
Thank you. I don't see any raised hands. That may mean that we can say thanks to Pavel. And
thank you very much.
Use our 10 minutes for making coffee. So wait us back in 10 minutes. Okay. Now we have a coffee making break. Well, hope everybody is already with his coffee or tea or whatever. And let's continue our work. And our next speaker is Dr. Marcel Blidner on leaf biomarkers.
Thank you very much. So I hope you can hear me well.
Yes, we can.
I try to start the presentation.
Fine.
Yeah, perfect. So welcome back from the coffee break and welcome to my talk. It's about the potential of leaf-wax biomarkers in fluvial sediment paleozoal sequences. And I would like to present you our case study or pioneer study from the Upper Alazani River in Georgia in the Caucasus region. So what is it about? Quantitative paleo-environmental reconstruction are key for developing a better understanding about past environmental and climate conditions. And in this context, leaf-wax biomarkers have been developed as a valuable tool during the last years or decades. And it was increasingly used in lake and marine sediments, but also in less paleozoal sediments. However, there are no studies investigating leaf-wax biomarkers in fluvial sediment paleozoal sequences so far. And this is a bit surprising because we found such fluvial sediment archives in many regions of the world, and they have the potential to increase our knowledge about environmental conditions in those regions. Therefore, our study aims to explore the potential of leaf-wax biomarkers in such fluvial sediment archives for paleoenvironmental reconstructions. And at the beginning, I would like to give you a short overview what leaf-wax biomarkers are and how we can use them in paleoenvironmental research. So basically, leaf-waxes are produced by terrestrial plants. They coat the leaf surface as a protection layer against environmental stress. And with the lithophore, they become incorporated into soils and sediments, and they stay relatively resistant there. We can now extract them from soils and sediments and analyze them. Maybe I have to mention that there are several different leaf-wax compounds. We concentrate or we're looking at the alkanes that are hydrocarbons, straight chain hydrocarbons. They are easy to extract and to analyze. In the first step, we can simply analyze the distribution pattern. You can see it here. Leaf-waxes mostly produce the longer chain alkanes from the chain lengths 25 to 35. They have those typical dominance of the odd chain lengths. And just from looking at the distribution, we can infer some information about the vegetation type, because the chain lengths 27, 29, they are dominantly produced by deciduous trees and shrubs. The chain lengths 31 and 33, they are dominantly produced by grasses and herbs. If you go a step further, we can reconstruct, or we can use the carbon and hydrogen isotopic composition of the single compounds to reconstruct hydroclimatic conditions. And finally, we can also date the leaf-waxes directly with an AMS. So we get a 14C age or a 14C signal that gives us the timing or the age of the leaf-wax formation. In the following, I would like to concentrate on the dating aspects of the leaf-waxes and also on the vegetation reconstruction. In the second step, we might have to take a closer look how the leaf-wax biomarker signal gets into the fluvial system. So we have to make some general considerations, and I therefore prepared a little schematic scheme. So let's imagine we are somewhere in the floodplain of a related hydrological catchment, and during geomorphic active phases, we have a lot of flooding, overbank sedimentation, and the leaf-waxes that are produced in the catchment, eroded from the catchment, those leaf waxes become deposited with the fluvial sediments. And to be honest, this can give them a certain spatial and temporal heterogeneity. Then, during geomorphic active phases, we have soil formation on the floodplain, and the leaf wax biomarkers, or the leaf waxes, they are directly produced by the local vegetation. They become incorporated into the soils and slowly overprinting the formerly deposited leaf waxes from the fluvial sediments. Then we have again some fluvial sedimentation and paleosoil or soil formation. So this is how we get two different biomarker signals or leaf wax signals in the fluvial archive, and we have to clearly differentiate between a catchment signal that is stored in the fluvial sediments and a local in situ signal that is stored in the paleosoils. And this is what we did in our, this is what we investigated in our case study in the Caucasus region. So I would like to briefly introduce you to the region. So we are here in the Caucasus region, located between the Caspian Sea and the Black Sea. We have the Greater Caucasus Mountains in the north, the Lesser Caucasus Mountains in the south, and we are specifically here in eastern Georgia in the Upper Alazani Valley. The catchment is quite steep. It rises up to 3,000 meters above sea level, and our investigated sequence is located here at 500 meters above sea level, where the river comes out of the mountains into the forelands. The study site itself, you can see here once on the photograph, and then here on the schematic scheme, we have those fluvial sediments and the intercalated paleosols. The recent soil and 3 paleosols are intensively developed soils. The 3 paleosols in between, they are only less intensively developed. This is supported by some sedimentological proxies. During soil forming phases, we have higher total organic carbon and also magnetic susceptibility values. And in contrast, carbonate contents and pH values decrease. The chronology of the whole sequence is based on 7 14C datings of charcoal pieces. You can see they are in stratigraphic order and spanning the last 8,000 years before present. To further improve the chronology, we calculated the duration of soil formation for each paleosol, and this was simply done by a so-called soil development index. And this index simply compares the sedimentological proxies from the paleosol to the underlying fluvial material. We then used the uppermost 14C as a kind of an anchor point, because we know the uppermost or the recent soil must have been formed during the last 1,600 years. We will use this chronology, this charcoal-based chronology, as an independent chronology that gives us the timing of sediment deposition, where we can compare our leaf wax 14C ages. And another thing I want to mention here is that we found all over the sequence archaeological artifacts, also in the lowermost paleosol, which indicates that anthropogenic activity at our site starts quite early, around 8,000 years before present. So let's have a look about the leaf waxes in our investigated fluvial sequence. In total, we analyzed 24 samples, and I showed you the concentration here. The leaf waxes are present, and they have quite good concentrations, but you can see concentrations of the paleosols are higher compared to those of the fluvial sediment layers. And this confirms our expectations that there are differences between the catchment signal and the local in situ signal. The question remains here, are those leaf waxes stratigraphically consistent, or did we observe some possible age offsets between the sedimentation timing and the timing of leaf wax formation? And of course, how large are those age offsets? For this, we directly dated the leaf waxes. I show you again here the independent charcoal chronology, And in total, we dated 11 leaf wreck samples, 6 from the paleosols, 5 from the fluvial sediment layers. And what you can see here, only 3 samples nearly matches the timing of sediment deposition. The other ages are quite off. So they have several, or they have age offsets of several thousand years. This was a bit surprising at the beginning, but there are some courses that produces those age offsets. One important issue is that the NRK do not necessarily have to be of leaf wax origin or produced by leaf waxes. They can also origin from other sources, for example, from petrogenic sources, which means they are produced by organic rich or they derive from organic rich sedimentary rocks that are mostly fossil. And this is also the case in our catchment, because we have Jurassic black clay shales largely outcropped here in the uppermost parts of the Upper Alazani Valley. So those Jurassic black shales are fossil organic rich sedimentary rocks, and they give us a certain fossil bias. To account for such petrogenic biases, we extracted one black shale sample, and you can see here the NRKs are present at all chain lengths, but without those typical dominance of the odd ones. And those is a 14C that proportion that now unfortunately underlies our leaf waxes in the sedimentary samples. To get rid of those petrogenic contribution, we carried out a heating and a correction procedure. I would like to show you in the following. So here, first you can see just a sedimentary sample from the fluvial sediments without any pre-treatment. And the corresponding age is quite old. It's about 16,000 years before present. Now we heated the whole fraction overnight at 120 degrees. And you can see we effectively removed the shorter chains, and the age becomes much younger. It's now somewhere around 7,000 before present. Problem is now we have some petrogenic contributions left under the longer chains that we were not able to remove during the heating process. And for this, we correct with a constant petrogenic correction factor. This is simply derived from the Jurassic black shale sample. What you can see here, the age is again become younger. We corrected for the maximal possible petrogenic contribution, and now the 14C age should represent the true leaf wax 14C age. Doing so, let's have a first look only on the catchment signal. The ages I showed you before are already the heated one. When we do the correction factor, when we applied them, they become even younger, but still those age offsets, especially in the upper part of the sequence, they remain. And the most likely cause for this is that the leaf wax signal here is pre-aged, which means those leaf waxes are produced at some times, at some top point in the catchment. Then they stayed in the catchment soils for several thousand years before they were finally eroded and deposited with the fluvial sediments. And the most likely cause for those large age offsets is that we have the strongly increased erosion after 4,500 years, when human activity in the Upper Alazani Valley strongly intensified. This makes the catchment signal from the fluvial sediments a bit challenging in the paleoenvironmental interpretation, because it gives us some temporal heterogeneity we cannot really resolve. When we take a look on the 14C signal in the paleosols, we see that at least in the intensively developed paleosols, the 14C ages match quite well with the timing of sediment deposition, or let's say they fall directly into the soil forming durations. However, we observe some age offsets. There are some age offsets left in the less intensively, in the weakly developed paleosols. So what's important here is at the end the proportion of the in situ produced leaf waxes. And it seems that the long duration, the long soil forming duration in the intensively developed paleosols was sufficient enough to overprint all the formerly deposited leaf waxes from the catchment with the fluvial sediments. But it is not the case here in the weakly developed paleosols, because there a certain proportion of inherited pre-aged leaf waxes from the catchment is still present. So what we finally can do, we can the most robust paleoenvironmental information can be derived here from those leaf wax alkanes in the intensively developed paleosols. And this is what I want to show you in the following. So which paleoenvironmental implications can we derive? I show you therefore the leaf wax distribution. I told you before we extracted or we analyzed in total 24 sevens, but I only will concentrate here on the 11 sample points that have corresponding 14 CHs. And the distribution is expressed in a ratio called contribution crassus in terps. And it simply says more crassus with higher values, more deciduous trees with lower values. What you can see is crassus dominates the paleosols throughout the sequence. Crassus also dominates the fluvial sediment layers in the lower part of the sequence, but in the upper part of the sequence, the deciduous trees and shrubs dominate. And when we finally take a look on an age axis and compare those to other regional archives, we can see for the catchment signal that all of our data points, they cluster here in between 8,000 and 6,000 before present. We have those crest-dominated samples that have been deposited with the sediments before 4,000 years. We have those forest-dominated samples that have been deposited after 4,000 years. One thing that is important is the profound erosion history of the catchment, because after 4,000 years, parts of the forested catchment have been eroded. It also shows us that reforestation in the Upper Alasani catchment starts quite early, around 8,000 before present, which is in line with other regional pollen records that shows us some regional reforestation about 9,000 to 8,000 before present. The crest-dominated paleosols, they show the trend of crest dominance throughout the Holocene. And this is in contrast to other regional lowland pollen records. For example, here from the neighboring Iori Valley, where we have deciduous trees before 5,000 years, before today, before present. And the most likely cause for those differences are that we have a long-lasting history of anthropogenic activity at our site in the Upper Alasani Valley. So to sum up the presentation, we found leaf wax biomarkers in our studied fluvial sequence, but the leaf wax signal is quite challenging because the catchment-derived leaf waxes, they are pre-aged. They have a certain spatial and temporal heterogeneity. This holds also true for the leaf waxes from the weakly or less intensively developed paleosols, because they are biased from inherited pre-aged leaf waxes from the fluvial sediment layers, and we can only derive robust paleoenvironmental information from the leaf waxes in the intensive developed paleosols, because they match quite well with the timing of sediment deposition. Doing so, we observed that the catchment signal from the fluvial sediments more or less confirms the general trend of forestation in the region that starts around 9,000 to 8,000 before present, but it also outlines the profound erosion history in the catchment. And the crest dominance we see in the intensively developed paleosols. This is mostly the result from the long-lasting anthropogenic activity that our site experienced since the late Neolithic. And with this, I want to thank you very much for your attention, and I'd like to be open for questions. Thank you.
Thank you much. Very interesting presentation. Unfortunately, we have only 1 to 2 minutes for questions. I have 2, but I will ask people if you have any questions to Marcel. Okay, I see one hand, but I cannot. Oh, David. Yes, please.
Yes, hello. I'll put my video on for this. Hold on. I'll ask a question that I always ask when I hear about exciting new approaches in the Holocene. I'm sorry if it's not something you've thought about. Is there any potential for studying this sort of detecting leaf waxes in interglacial paleosols? Perhaps showing whether there was contemporary vegetation. I'm thinking of the Lurs soil sequences. Are those sorts of paleosols likely to contain leaf waxes?
Yeah, it is increasingly done in Lurs paleosol sequences so far. It's successfully done there, but yeah, so they have some interesting results out of it. I mean, also the hydrogen or carbon isotopes, they give you some more information about climatic conditions. So it's possible to use it there. But the problem is, I mean, what's the problem in a lot of archives is those pre-aging or the potential pre-aging of the leaf waxes. So I think it's often necessary to date them directly to get an idea if you have a lot of transfer times through catchments. And on longer time scales, you lose the ability to date them directly, right?
Okay, thank you.
Thank you. And the last short question from Maria Bronica.
Yeah, thank you for your very interesting presentation. I would like to ask, what was the temperature of heating when you tried to get rid of the old fractions of leaf waxes, and how did you determine the needed temperature?
Yeah, so I didn't get the first part of your question. Could you repeat it for me?
What was the temperature of heating?
Yeah, the temperature.
Yes.
We heated them on 120 degrees.
Yeah.
So for 8 hours.
And why exactly this temperature? How did you determine the needed temperature?
Yeah, we played a bit around. So we started with 60 or 80 degrees.
Yeah.
And then we increased it a bit, and we see with lower temperatures we get not rid of all the shorter chains, and when we go over 120 degrees, then also we lose something of the longer chains. So it
was just experimental approach.
Yeah.
Yes. Yeah. Thank you. Thank you
much. Unfortunately, we have no more time for questions. I will ask my questions during discussion. Marcel, how you will join us to discussion. Thank you much.
It was a bit long. Thank you.
Yeah, no. Well, our next speaker is Ngaye with the presentation on landscape dynamic through luminescence methods. And please.
Yeah, I'm sharing. What
yes,
are you
fine.
seeing?
Yes, we can see.
You see the full screen?
Yes, we see the full screen.
Yeah. Okay, so hello everybody. I'm Anne-Guyez. I'm doing a PhD in Toulouse, in France. I'm supervised by Stéphane Bonnet, Tony Rayman, and Jacob Wallinga, that are geomorphologists, and Tony and Jacob are more into luminescence. So what we are trying to do is to use single grain luminescence to better understand the past river dynamic of a specific river, the Rangitiki River in New Zealand, since the late glacial. So quantifying past river dynamics, it's a challenge for geomorphologists. They want to have insight on sediment pathway, storage time, and sediment sources. It appears that among appropriate tools, luminescence could be really useful. It uses an intrinsic mineral property, so every grain can be a tracer, and recently major efforts have been made to to test the potential of luminescence to better constrain geomorphic processes. There was a study in 2019 of Bonnet that succeeded in revealing the landscape dynamic of the same river. So this study is a follow-up of what they've done. There was also a review from Gray that shows the potential of luminescence to extract transport information from river sediment. So today I'm gonna take you to New Zealand. So here is the river I'm studying. It's the Rangitiki River here, located in the North Island of New Zealand. The river runs through the Whanganui Basin, which is quite homogeneously composed of Pleistocene marine deposits. The catchment is composed of the Rangitiki and 3 major tributaries, the Moafango, the Aotapu, and the Kafatao. Long-term incisions have been interrupted by period of climatic aggradation that have led fluvial field terrace, T2 and T1 here. You can see the yellow and red terrace. And you can see that T1 defines a wide corridor along the river. And since T1 abandonment, there was 75 meters of incision and creation of post-T1 Holocene terraces that you can see here in orange. There are many, many terraces. Actually, it's my background also here, many terraces. The river presents a major nick point that is located here, where you see the blue star. And below this nick point, the river is defined in 2 sections. The upstream one here, that present a canyon shape with high valley wall. You can see here the wide surface of T1 channel and canyon with high bedrock walls in light gray here, with T1 on top of it. And the downstream section, which is here, that is where all the terraces formed during the Holocene are formed. The post-T1 in orange here are only located on this section. And this section is also characterized by a larger river width. So this makes this area a great place to study Holocene event. So what we've done is we've been to the field to sample for luminescence. We collected and measured 28 new samples distributed along the river, among which we took T1 terraces, post-T1, and also modern sand. And we use single grain post-IR protocol at 175 degrees. The single grain discs were loaded with feldspar grain and measured. What we obtain for each grain is a dose response curve. For those of you that not really aware of what gives luminescence, it's this type of response. And then you have an equivalent dose for each grain when you do single grain, which you can transform if you have the dose rate of the surrounding, you can transform it in age. So there is 3 types of dose response curve. The first one, type A, is the classic young grains that come from a terrace or modern sand. Its dose is below 100,000 years. And there is type B and C that correspond to a particular state that a grain can reach, which is saturation. The signal can either be above a certain threshold here, or too high to be projected on the dose response curve. Then, when we measure one sample, we obtain this kind of distribution. We contain saturated grain and well-rich grain, which are the grain with the lowest dose. And those 2 types of grain are easy to identify for us. Then we identify the processes that can modify the signal of the sediment mix in a fluvial system. First, there is a longitudinal bleaching. So because luminescence is, when you measure a grain, you suppose that the grain were exposed to sunlight, but in fact, the longitudinal bleaching can be complete or partial. It concerns the grains that are exposed to sunlight and lose some signal. In second, there is a lateral input of saturated grain, most likely through landslide. And in three, the remobilization of grain that has regenerated in former floodplain fluvial deposit. Then what we do here is we look at different samples along stream, and we can see how their dose distribution is changing and try to relate this to those three processes I just told to you about. So in this study, we look in detail into the well-bleached grain first. We use them to date as a classic luminescence approach to date T1 and post-T1 terraces and reconstitute the river incision. So here on this graph, first, we can see that T1 terrace, it's a red triangle here. They have ages between 11 and 17,000 years. Then the Holocene post-T1 terraces are separated in two groups. The highest three here mark the initiation of the incision, while the lowest define a linear trend at 3 millimeters per year here. In fact, what is really interesting is that those terraces here, those 6, among which 4 are located here on this area, are all at the same place. We see that the highest post-T1 terraces are dated at 10 and 7.7 thousand years. And we've got a gap here. And the two lowest at 28 and 18 meters here, above the present riverbed, are dated at 6.9 and 6.8 thousand years. So what we think is that the major nick point that is now located further upstream pass here between 7.7 and 6.9 thousand years, which correspond to such river profile. By that time, it means that to go from terrace at 60 meters to terrace at 28 meters, the river has to incise vertically very fast at a minimum of 15 meters per year, which is 5 times higher than the 3 millimeters observed afterwards. The nick point has then propagated of 64 kilometers to get where it is now, which corresponds to a nick point migration speed of about 9 meters per year. Then we look at another proxy that that single grain can give you, the number of saturated grain. So you can see here that this is the number of saturated grain in each sample in percentage, plot against the relative elevation of terrace above the present riverbed. So on this graph, you can see first that T1 is acting really differently than the orange one. T1 has very low amount of saturated grain. And then you see a peak, a maximum for mid-elevation post-T1 terraces, reaching 65% of saturated grain, which is huge. And we observe that this proportion decreased through time in the Holocene post-T1 terrace during the linear incision. That was already a very interesting result. But we also look at the data longitudinally. And we took those 4 terraces here that we look longitudinally, and we see that from upstream to downstream, the saturation is increasing. This is visible here by the gray area on this graph that show an increase from 40 to 60%. It means that for the same river profile, we've got more and more saturated grain along stream, which can be explained by only one process, the lateral input of bedrock grain along the river, most likely through landslide of valley wall. So what we think is that after the nick point has passed, it has created valley wall, integrally in contact with the river, prompt to provide directly saturated grain into the river. Then if we look at the rest of the terrace here, for example, if we take the one between 10 and 20 meters, we see that the saturation is not increasing, especially toward downstream. So what we think is that it has to do with the numerous abandonment and preservation of post-T1 at this elevation, like that, which limits the direct contact of the river with its wall, and therefore the input of saturated grain in the sediment mix. To conclude, our study shows that geomorphic processes have a strong impact on the distribution of the luminescence in fluvial deposits, and in particular, in the amount of saturated grain. Our study also confirms that luminescence could be a powerful tool to give insight into geomorphic transport processes. Thank you for your attention. I don't know if you have any questions. I think there is a bit of time left.
Colleagues, please, your questions to Anne. Professor Cunha.
Yes, quite interesting presentation. How you can discriminate between different dynamics of rivers, because there are rivers they are quite flashy, so they have a very intense period of transport and erosion. So in some cases, during the evolution of a river, it can pass from a steady stage of continuous discharge to another period that is more flashy. So this flashy behavior can provide more grains with partial bleaching, because it can erode lower levels of the riverbed, and also if the water is turbid, of course the bleaching will be more difficult, and only the sand that will become on the top of the riverbed will be bleached. So are you dealing with this topic?
Not really, but I think you're right. It can be, but what we think is that I think it has been there has been flash flood all along this 10,000 years, but because we see such a big difference in the saturation, I think there was something else more than just a flash flood. So we think it has to do with the canyon shape, but yeah, I think there is also incorporation of material even right now. It's just less than what it used to be.
Okay.
Thank you. Other questions? Okay, let's leave other questions for discussion. Thank you, Anne.
Thanks.
And our next speaker, it's tomorrow. Willem Tunen. Willem, you're here. Fine. Radiocarbon data for lower worse river deposits. Thank you much.
Can you hear me?
Yes.
Yeah. Right. Let's put that up.
You can see you.
Yeah.
Yeah.
All right.
Fine.
So thank you, André. First, I want to thank my colleagues, Marjolein van Noord, Hessel Wodderink, and Kees Kassen for collaborating in this project. First, some facts about the River Meuse, the Meuse catchment. It's in northwestern Europe, and it's about 36,000 square kilometers wide. The most drains areas of France, Germany, Belgium, Luxembourg, and the Netherlands. And normally the Meuse has an average flow of about a bit more than 300 cubic meters per second. Its floods, they mainly occur during late winter, early spring, and it's a rainfall-dominated flooding regime. So it's much affected by the North Atlantic climate system. It brings depressions with a lot of precipitation to the catchment, and together with some snow melt, that generates the bigger peak floods in early spring. Now, something happened a few months ago, and which was a bit of a surprise, because it wasn't one of these typical winter or spring floods. It was a July flood, which are quite rare. But as we've all seen on the news, they were quite hazardous. So this specific event generated over 10 centimeters of rainfall in this region in Belgium and Germany. And it generated a record discharge for the Meuse, and not just a record discharge in terms of peak floods in normal wintertime or spring floods. This was a summer event, so it's even outside the normal flooding season. It generated this extreme discharge. And as we've also seen in the news, there was severe damage in the upland regions. Luckily, in the Netherlands, the damage was less extensive. So what happened? What generated this flood? Well, people more or less agree on it right now that there was a weakening of the jet stream, which caused a locked-in situation of this depression, and that's how it could generate these huge amounts of rainfall in a small area. And the overall setting for that was produced by a weakening in the jet stream. Elsewhere, for example, in the US, that generated a huge drought, and also in Siberia, the same setting, locked-in setting, generated a prolonged drought with forest fires. Up till now, climate modelers and policymakers, they anticipated that such a situation as happened this summer, that it would not really occur or not be likely to occur before 2050. Well, it's not certain, but it's likely that, well, it seems that the river is responding more quickly, and the climate is also changing more quickly than people anticipated. This shows, however, that there is a necessity, because there's an uncertainty in what's happening, how are these responses occurring. So there is a necessity to study the fluvial archives for a reference to see if these fast transitions happened before and what their magnitudes were. And our weapon of choice here, the method that we deploy to look at the long-term changes of the fluvial system, is a CPDF, a cumulative probability density function. Well, first of all, it's an ideal method to deploy during COVID-19 because you can do it from home. You don't have to go into the field. This method depends heavily on already existing data from previous dating. So what is done here on the upper right figure is that you have all kinds of dates from a fluvial setting, and basically what you do, as done here is in Oxcal, is to use a sum function. So it sums up all the individual ages of each individual date, and that kind of combines it into a overall view on dated deposits from the catchment. And I will show you later on what you can derive from that. Of course, you can use kind of the bulk method, that you use all data available in the fluvial setting, but you can also make subgroups to investigate specific topics. So you can divide them according to sub-environment, levee, floodplain, or channel datings. You can differentiate between dated materials, for example, AMS C14 materials, so organics, or the more clastic deposits, which have been dated by OSL. And you can also integrate other types of information, by the way, but normally it's only C14 and OSL. You can subdivide your data set into different subregions, so you can actually compare what's going on in different regions in the catchment. And you can also divide the data up to lithological context. So normally what you have in a publication is you have a C14 data or an OSL data, and you know exactly what the lithological context for it is. Is it a single event, or is it a change date? So is it placed on a lithological transition? Or, for example, with the radiocarbon date, is it placed in the center of a thick peat layer, which is kind of an indicator for long-term stability of the environment. The same applies to soils, for example, if it is placed in a soil or not. So that gives you a tool to differentiate between periods of fluvial activity versus stability in the landscape. In this data set, which I'm going to show right here, I just used the bulk approach. We have to do future work on this and further make these subdivisions. But as I will show, you can already see quite a lot from this bulk assessment. For the Muse, we gathered almost 250 dates, 163 radiocarbon dates and 82 ozell dates from the lower Muse, the alluvial Muse in the Netherlands, which is outlined on that right figure. And we gathered our data as a data mining exercise from studies of fluvial geomorphology, archaeological context. So often when they do excavations in the setting, they date river sequences as well. And over the last decades, there have been a lot of flood management projects, which also involved some dating of fluvial deposits. So at the bottom, that graph, that's our first result. So that's all these dates, about 250, grouped together in this summing function. And you can see that there are some big trends there, but also some smaller phases or kind of event-like occurrences in which the dates of these fluvial deposits, they cluster or they are more winnowed, more spread apart. If we look at the late glacial to early Holocene period, there we have an increase, a sharp increase of our C14 dates during the early Allerate, and it stays highest during the Younger Dryas, but during the second part of the Younger Dryas, it collapses a bit. Then it rises a bit during the early Holocene, and during the later Holocene, the PDF becomes lower again. So there are fewer dates falling in that general period. Overall, in that late glacial to early Holocene period, we have low CPDF values corresponding to colder phases and higher CPDF values corresponding to warmer intervals. We don't have a clear representation of the bulling interstadial, so the first warm periods after the late glacial. And that corresponds more or less to also individual observations from studies in the Lower Muse Valley, that often the bulling interstadial is not very clearly represented. And the first real change in river system and a very clear representation in geomorphology comes from the Allerate period. And then also in our CPDF, there's apparently a two-stage Younger Dryas event. First, there's a peak in the CPDF, and then it collapses completely. And some people have suggested that the Younger Dryas of Northern Western Europe and also Northern Europe is a two-stage event. So it starts off being cold and wet, and becomes during the second half, it becomes cold and dry. Now, how to combine that, how to interpret those CPDFs and tie it with fluvial geomorphology. What happens is, of course, you have shifts in fluvial style. So during this late glacial, early Holocene transition, you have incision going from the late glacial up to the early Holocene, and higher terraces become abandoned. Those are quite well preserved after that abandonment in the landscape, and they can be easily dated still today. Also in the Allerate period, for example, the river shifts to a meandering pattern, and temperatures also become warmer, and these abandoned channels in which vegetation can grow in this warming climate, they preserve organics which can later be dated with radiocarbon dating. So temperature and river style, they are reflected combinedly in this CPDF analysis. And the trends that we see, that they more or less follow what is already known, of course, from previous studies on the Muse, from the succession, this climate versus fluvial succession. And then there's also a researcher bias, because there is a focus on this late glacial to early Holocene transition. A lot of people have taken dates at those sites, so there is quite a large number of dates falling in this period. So that's why this whole period is quite high in the CPDF, because lots of studies generate lots of dates, so a higher probability of a date falling in that period. So you have to consider that as well. So if we go to the Holocene, this CPDF has an overall decrease during the first half of the Holocene, and then values become slightly higher during the Holocene climatic optimum, so between 8,000 and 5,000 years ago. And then in the last bit, the last few thousand years, so more or less since the Bronze Age, we have an uptake in our CPDF. So more and more dates fall in that period. First, the declining trend. How do we explain that? Well, some suggestions, or it could be that we have a stabilizing vegetation. So the catchment, in the warming climate, there is a steady growth of vegetation. The forests become more denser, and it becomes less variable. So once you have a establishing vegetation, it fixates the catchment. So that's also the study by Mottel et al. Shown on the top right, is that the rate of vegetation change in catchments of Northwestern Europe, it decreases dramatically during the earlier part of the Holocene. This stabilization of the landscape, it fixes in water and sediment. That's probably how you can connect the CPDF with these overall trends, that the river system becomes a very stable system because there's fairly little variations in sediment and water during this period. And also there is probably a slight cooling and drying of the climate during the Holocene, which may have affected the formation and preservation of organics as well. Then there's this increasing trend in the last few thousand years. And of course, a very obvious reason for most recent deposits is that preservation is pretty high. Not enough time has passed ever since to erode these young deposits. And also with the fixation of the river channel, well, at the current state, that preservation potential is quite high. But then you see a trend which kind of picks up about 4,000 years ago, and you can see it in the CPDF, but you can see a similar direction of change in the vegetation reconstruction by Mottel et al. And that is connected to deforestation of the hinterland. So in about the Neolithic to Bronze Age period, people start to clear the forests, and that actually generates more erosion and sediment input to the catchment. Also the buffering function of the vegetation, it decreases for precipitation, so more runoff is generated as well. So that's reflected in the activity of the system. So more sediment, more water means more morphology is created, more changes occur in the alluvial setting. So more spots become available, like abandoned channels, to preserve spots of organic that can be dated. And of course, there is because we depend also on archaeological reports, you can see that there is an uptake in dates which are related to the Roman period and afterwards as well. So there's again this researcher bias involved as well in this uptake in the last few thousand years. Now, there is also this apart from these large-scale trends, there are these episodic changes and events. And we performed a wavelet analysis on this data series, and it shows, quite intriguingly, it shows a significant periodicity of uptakes and decreases in the CPDF, which centers us at around 290 to 360 years, and also some multiples of that value. And it's quite persistent. So the graph, the top graph, the regions outlined with the black line, those are significant results. And you can see that the periodicity of about 300 years, that is significant between about 8,000 years ago and 3.7. And again, later on, it pops up again. So during a quite substantial part of the Holocene, you have this ongoing oscillation or kind of variability. And we also can see some quite interesting peaks in the CPDF, which may relate to bond climate events or IRD events. One which is very clear is about the 8.2 event. So it seems, and which is also kind of logic, that large disturbances to the North Atlantic climate, that they are indeed reflected in the CPDF of the Meuse. So the North Atlantic climate, it disturbed the precipitation, the depressions going over northwestern Europe, and it triggered probably some big floods, which generated changes in the landscape, which are again reflected then in the CPDF that we have. A recent reconstruction by Fei Peng et al. In 2019, they made a reconstruction of flood deposition, or well, deposition of the Meuse based on a levee site, and their phases of increased sedimentation on the levees, they also agreed quite well with our CPDF. So there is quite a good correspondence between these individual studies focused on a single site and this approach, which covers kind of the whole alluvial valley. So as an outlook, as I said, this is a first dump of data for which, well, I showed several explanations, but we need to dive a bit deeper into this. What we particularly want to do is to group this data, to analyze them according to their what they represent. So are they stability dates or are they change dates? And well, already a preliminary result is that a lot of these very high peaks, for example, the 8.2 events, nearly all of those dates are really change dates. So they relate to changes in the lithology of these settings where they have been recorded. And then also the stability change date analysis, that's the traditional approach to reconstruct flood regime changes. Then the next step is, of course, to compare it with other climate proxies in the region and also with other CPDFs from river systems in the region, if they turn up, if they have the same kind of dynamics in there. And the last obvious thing that we should do is try to see if we can find an explanation for our periodicity analysis. So does it tie in with a specific element of the North Atlantic climate system? Do these periodicities exist in the NAO, AMO, or another system that is active? Or is it a more direct relation to solar impact? To conclude my talk, well, the CPDF, it produces a very holistic view on fluvial change. So it groups together basically everything that goes on, and what you can see, these big trends in the graph, they are a combination of various factors. So they are human influence, they are climate change, but if you have enough dates to generate this picture, you get really this significant phasing in there, which is interesting to look at and to study further. Then also, because this is a regional approach, it is a good support of more localized studies. Sometimes you can, in local studies, you can see a lot, basically more than in this regional approach. But also locally, some events might be missing, some part of the record might be eroded, or just locally the sensitivity of the setting is not suited to record a certain signal. So I think this is good, and also tying in with the recent flooding and the changes that we might expect in future climate. It gives a very good overview of all kinds of different factors that can influence the river system, and how soon or how fast or how great the magnitude is of its changes in response to these perturbations. Now, for the Meuse CPDF specifically, it is a very nice way to illustrate the changes that occurred during the late glacial to early Holocene period. And in other CPDFs of North European or Western European river systems, the late glacial early Holocene period is not that clearly represented. So that's a bit of a novelty for this data set. And then again, as I showed the periodicity analysis, it's intriguing because it shows that there is an intrinsic part of the fluvial landscape evolution which evolves according to periodicities. So it would be good to if we could find out what the reason for that is. Then again, yeah, as I said before, with this intensification of the flooding regime during climate change, and also with a lot of human alterations to the catchment, such records, they can really demonstrate how sensitive a river system is to these different kinds of perturbations. And for example, for the Meuse, it's quite obvious that both climate change, but also human action, that it is really important for the changes that occurred during the Holocene. So it seems likely that also during the Anthropocene and the future centuries, these factors will remain very important. So that's it. Thank you.
Thank you, Willem. Questions, please. Hans?
Yeah, thank you very much, Willem, for this interesting talk. And I liked very much your comparison of the OSL PDF and the 14C PDF. Yeah, because as I thought to see is there is a time lag for the last millennium between the OSL sedimentation ages and the radiocarbon ages of some millennia, probably linked to inheritance of organic matter in the fluvial sediments. Yeah. And with this respect, I found also very interesting the period between around 8.5 and 5,500 years, but also between 4,000 and 3,000 years, yeah, where we see large peaks of the radiocarbon plot, but no or almost no peak of the OSL plot. So my question is now, do you think that this could maybe be a bias for the radiocarbon signal? That means this was the Neolithic period, the first one, and the second one was the Bronze Age period, that during those periods, a lot of fluvial of organic material was eroded, incorporated into the fluvial system, and then it was when it was dated with radiocarbon, you actually date a younger event, but however, the organic material is old. Yeah, so, yeah, that's my question. Do you have some indications for this, or maybe parallel, also direct parallel datings from these periods of OSL and radiocarbon? So what do you think about this?
Yeah, thank you for that question. That's a good one. Because this is a bulk approach in which we basically depend on what's already there. There's not so much information to really compare one-on-one the dates from radiocarbon with OSL. However, and then also for radiocarbon dating, some of the older reports, the older studies, they use bulk dating, which is dangerous for this kind of exercise. Compared to the more recent studies, they use the for example, a single seed or really picked out specimen, which are really good. And those samples, they avoid that problem which you mentioned, because we know they can't be eroded from the upstream catchment and be older carbon introduced in the system again. Now, another problem here is the range of dating between the two methods. The OSL dating often has a 10% uncertainty range. And if you go back 10,000 years, that becomes a problem, because that's also why this OSL curve is smeared out in the past, in the older period, and it becomes much more confined to peak much higher in the more recent period, because a thing is 100 years old and 10% of that is only 10 years. And that's much better than the radiocarbon date at the same interval. While if you go back to the late glacial, the radiocarbon date, if prepared well, is much more accurate than the OSL dates, which goes in this kind of exercise. So before even arriving at an answer to your question, these are all kind of things that go into this and which have to be considered. So yeah, to give an answer to you, yes, this will occur and it will be present in this kind of records. And that's why it is important that you collect a lot of dates to kind of filter this out, this random noise, which is induced by maybe erroneous dates. So in this record, this is 250 dates, but that's also more or less the minimum that you need to generate something which is worth discussing. Apart from that, you really have to scrutinize the original data from which report comes in. I know somebody, a PhD from Groningen, I think, Groningen University, is working on also a classification of this kind of information according to age in which the report was generated. So to filter also out the bulk dates from the 70s and 80s, 1970s and 80s. And if you, for example, split up these groups of radiocarbon dates into modern AMS dates and older bulk dates, and you compare those, then you might come to an answer to your question. So it might be worth testing that based on another division of this data, according to what you suggest. But I'm not sure if we have enough data to really be really specific on that answer if we try that.
So maybe I give a very short reply. Yeah. So okay.
Hans, maybe you leave it for the discussion. Sorry.
Okay. Sorry.
Short of time, and we also have to ask one more last very short question from André Kirchner.
Thank you, and
very short answer from Willem. Okay.
Yeah. Let's speak later.
Okay, André.
So, hello. If we are looking to comparable studies like the famous one from Hoffmann et al., for instance, and if we are then looking just to the floodplain ages, I was really surprised, and really in your data set really nicely is that the rapid events come out very nicely. Do you have an idea why we haven't, or why in this comparable studies these Holocene rapid events are not that present as in the floodplain? Because in Hoffmann et al., for instance, the colluvial dates, they trigger, or they somehow show this rapid events during the early Holocene, but the floodplain ages actually do not show them. And do you have an idea why it seems to react, the MERS seems to react different?
It might be in the setup of the catchment, so the physiography. What we saw with the floods last summer is both the Rhine catchment and the Meuse catchments were affected by these storms. But the Meuse is a much smaller and tighter catchment with much steeper valleys in these small regions in Belgium and in France and in, well, it's part of the Ardennes specifically. And that really has a more flashy nature to the flooding and a lot less buffering function of the Meuse compared to the Rhine. So the Rhine is much bigger as a catchment, but also it has a bigger capacity to buffer kind of these big events. So probably because the setup of the Meuse, these floods, these events are much more violent and much more responsive to these rainstorms. So I think there's an explanation in that.
Thank you, Willem. And let us switch to the last presentation before lunch, Willem, could you remove your presentation?
I'm trying.
Good. Okay. Yeah. Thank you, fine. Alexander Gergiadi, the Volga and the Don water flow in warm climatic epochs. Fine, we can see.
Okay. Thank you, Mr. Chairman, and good day, everybody. I would like to present our result concerning water flow of large Russian rivers in warm climatic epochs in geological time and in the future scenario, future climate, and for recent period. So the features of the Volga and the Don river runoff changes during the Holocene optimum, as well as scenario conditions of global climate warming in the current century, and the Volga river runoff changes in the warm epochs in 3,000 and 9,000 years ago were revealed. Paleoclimatic reconstructions based on data of spore and pollen analysis of fossil lands and on calculations carried out on the ensemble of the global climate models of PMIP2 program, as well as the paleoclimatic reconstruction based on the results of experiments on the global climate model of Moscow State University. Scenarios of climate warming in future performed on the ensemble of global climate models of CMIP3 program. So hydrological changes were evaluated on the basis of the monthly water balance model. We also compared the scale of above-mentioned changes with the modern observed differences between runoff typical for long-term periods of decreased increased runoff based on observational data for last and current centuries. So here you can see Volga and Don basins. As you know, the 2/3 of the Volga basin are covered by taiga and mixed forest. And Don basin is dominated by steppe and forest steppe. The main part of natural landscapes has been transformed by anthropogenic impact. The water regime of the Volga and Don has also been changed by numerous reservoirs. But we naturalized river runoff of these rivers for comparing with the runoff in the Holocene and future climate. So, about characteristics of paleoclimatic reconstructions. We use data of paleoclimatic reconstructions, deviations of air temperature and precipitation for January and July from their modern values. They were obtained the basis of zonal and information statistical methods. Hydrological assessment were carried out for two variants of paleoclimatic reconstructions. In one of them, the absolute value of the statistical error was added to the deviation of the climatic characteristics. And in other case, the statistical error was subtracted from the initial deviations. Data on January deviations were distributed for months of the cold half year and July for months of the warm half year. Model paleoclimatic reconstructions of the average monthly anomalies of the above-mentioned climatic characteristics for each month of the average annual year were obtained by averaging the results of restoration carried out on 18 global climate models, included in the PMIP2 program. And also, I said earlier about results of paleoclimatic reconstructions made by climatic model of Moscow State University for 3 times time periods of the Holocene. About projected changes, the range of probable climatic changes, which is estimated by calculating mean annual deviations of climatic elements for the 2 or 10 to 2 or 3, 9 period from the recent values. Calculation results obtained by using the global climate models for CMIP3 scenarios. So we use these results, and the calculations of water balance model are made for the 2 scenarios using the most and the least intensive rises of globally averaged air temperatures. The 10 best climate models, which were chosen by Kislov with colleagues from 23 climatic models, by comparing the present-day observed climatic conditions with the simulated ones in case of CMIP3 are used. The range of scenario deviations of mean monthly air temperatures and precipitation totals is determined for each of the scenarios ensemble mentioned by averaging the calculated results obtained from each of the climatic models chosen. So we use the model of water budget of river basin. This model is based on conservation equation of average long-term monthly water balance of river catchments. In general, it can be written for each cell of regular grid in the following way, at the well-known equations. This model simulate main processes infiltration and moisture accumulation, formation of surface, subsurface groundwater flow, evaporation, water accumulation, and snow cover and snow melting, and so on. So here you can see results of our calculations for the Holocene optimum period and for future climate for 2 time periods. So, dotted line is deviations from modern values for runoff, annual runoff. A thick line is deviations of precipitation, and thin line is deviation of air temperature, annual air temperature, for different cases. One is the Holocene optimum according to PMIP2 project, 2 and 3 for Holocene optimum reconstructed by traditional methods for the 2 cases which I explained earlier, and 4 is values for recent climate. Right ordinate is for temperature, left ordinate for river runoff and precipitation deviations. So, and we use results for 2 types of scenarios, B1 and E2, for 2 periods. As you can see, Volga and Don River runoff, air temperature and atmospheric precipitation for scenario climate are higher than their modern values. It's obvious. During the Holocene optimum, air temperature and atmospheric precipitation are higher than their modern values also, but river runoff could be lower than modern one, Volga and Don, if we based on data on traditional paleoclimatic reconstruction, or equal it in case of Don, or higher than modern value in case of Volga based on PMIP2 paleoclimatic data. So here you can see changes of intra-annual distribution of water flow for every month of year, and dark blue color is modern values, and lighter color is projected values for 2 cases. If you consider then that on the Volga, the flood wave shifts slightly to early dates, and the runoff is distributed for the months with the highest runoff at April. And on the Don, on the contrary, the flood wave spreads and out, and at the same time, the flow per month with the greatest flow decreases. At the same time, the winter runoff increases slightly both on the Volga and on the Don. So here you can see also results of calculations of river runoff changes for Holocene optimum period, and this is 3 positions in this table. One Holocene optimum according to PMIP2, and 2 other according to traditional methods reconstruction of climatic characteristics. Left part is for year, for runoff for whole year. Next one is deviations for flood. Next for winter period, and last for summer autumn period. And according to reconstruction based on PMIP2, paleoclimatic data, flood runoff as well as runoff for whole year was higher as a modern one on the Volga, but based on traditional paleoclimatic reconstruction data, it was decreased slightly. The same picture we can see for future runoff. Runoff for low flow seasons is higher than modern one as for the Holocene as for future climate. Flood runoff for Don River is lower than modern runoff in the Holocene optimum and in future climate. Runoff for whole year for Volga was higher than modern one. Runoff for low flow period is significantly higher. You can see here, higher for than modern one, especially for winter season in the Holocene optimum, as well as for future climate. The similar picture we can see on the Volga for sub-Atlantic Holocene optimum and early boreal warming based on MCU model paleoclimatic reconstructions. You can see deviations from modern hydrographs values, and you can see this picture is rather similar for different periods, but these periods are different by scale of deviations. So also we compare river runoff for these two rivers for two periods during observational period. This periods are different by climate. First one was rather cold climate, and second one beginning from approximately 1980s is warm climate. And here you can see values for annual runoff and flooded winter runoff for reference period for relatively cold climate for Volga and Don. And in the right part of this table, you can see the changes in average annual runoff in the period of modern climate warming. And also as Holocene and in scenario changes, scenario projections, we can see that in this case, we can see the similar picture in comparing with warm climatic epochs in the Holocene optimum and in future climate. Flood runoff is increased insignificantly. Volga, in case of Volga, or it is much higher than in colder climate, in case of Don. Winter runoff is increased significantly in both rivers in warmer climate. You can see especially for winter runoff, approximately for 45–50%. So conclusions, the conditions of the late Atlantic optimum of the Holocene reconstructed from paleontological data are the closest in terms of scenario thermal regime in the Volga and Don basins, characteristic of the first third of the current century. At the same time, the annual river flow of the Volga and Don, according to the results of calculations on model of the monthly water balance, turned out to be lower than modern one if is used data on traditional paleoclimatic reconstruction. This result is consistent with the paleo river flow estimates for the Holocene optimum obtained earlier for Volga on the basis of zonal dependencies of the annual runoff with climatic characteristics and with the results of the reconstruction of the runoff from paleomeanders. Under scenario climatic conditions and paleoclimatic reconstructions, based on ensemble of climate models of the PMIP2 program, it turns out to be higher than the modern one on the Volga, or almost does not differ from it on the Don. In the conditions of the climate of scenario future in the first, third, and middle of the current century, the annual flow of the Volga is likely to increase as the climate warms, while the flow of the Don will remain almost unchanged. These results were published in this book and several papers. Thank you for your attention.
Thank you, Alexander. Any questions? I have one. We usually say that the Holocene climate optimum is the analog for future global warming conditions. But on the first graph you showed, we saw that according to the calculation on climatic models and other reconstructions, in the climatic optimum, the river runoff dropped, but precipitation rose in relation to the present.
Yeah.
And when we see all the calculated scenarios for the future, runoff and precipitation rise both.
Yeah.
So can we conclude that the Holocene climate optimum is not the analog for future hydroclimate changes?
Yes, you are right. If we will talk about both about river runoff and climatic characteristics, especially precipitation. Yes, but it's true for annual values. But for understanding why we see such differences, we should analyze interannual distribution of changes, climatic and river runoff.
Thank you. I see no other hands. Okay, good luck to these white bears in the global warming. Thank you, Alexander. Let me make a short announcement before we go to lunch. We did not, so we meet here in an hour and a half. You all have the program. We did not plan to switch off the conference for the lunch, but unfortunately, few participants have entered by different nicknames and they were rejected by the organizer, and system does not allow them to be in. So it remembers their IP address and rejects them automatically. That's why we have to switch off the conference and reset it for the after the lunch. So I kindly ask everybody to enter once more in the end of the lunch time. The conference will be launched in an hour, so half an hour before the end of the lunch break. Thank you, and I encourage you to enter under your own names, please, because we are very anxious about the hooligans. We have very bad experience about that. So thank you, and see you in half an hour and a half. Bye.